title of the conference, which is recent methods on machine learning and data analysis. Maybe it's not the best possible title for our conference, but we will adjust next time. So that's some key points of the conference. Also, what I want to say that I suggest once you start your presentation, you briefly introduce yourself, something like saying name, where you are from, and then what you are doing very briefly in general, just one sentence, and then you start your presentation. So something like that format. What is important, despite our conference is friendly and informal, still we need to keep in time. So please keep in time. And I just want to remind the presentation time itself should be expected to be lasted from 10 to 15 minutes, and then some time left for quick questions and also switching to another presenter because it takes time to unmute microphone, etc., etc. By the way, please always keep your microphone off when you are not talking, because sometimes that disturb other people. And please, again, please respect your colleagues, your friends, and keep in time not to change our schedule. So that's actually all the introductory notes I want to say. During the conference, we can share different opinions and discuss some points, because we expect at the end we will have some spare time. And now let's just go. It's just 3 minutes, so I saved the time actually. Then I will say something else, what is important. By chance, just occasionally, today morning I was listening sort of lecture, because the title of lecture attracted me very much. It is about happiness. Happiness, because health and happiness is something what everyone wants to have. And then in the United States, they conduct very long-lasting study which is lasted 75 years. And it was a very sophisticated, very detailed study of very different factors, etc. And what they find out, the conclusion, one of the conclusions of this study was that okay, health, even health and happiness actually coming when the person is communicating, from communication, from social links, etc. It doesn't mean there should be so many of them, not necessarily, but they should be good relationships. And then even the health is influenced to the health even. So I think with our conference, we will somehow go this way and maybe even make our life more happy and healthy. Let's see what's happened. Okay, now let me, there could be, by the way, there could be some technical delays. So if we delay with someone, then we just over this presentation and then come back to the next one and then back to this one, because some couple of students now in our building, and they are just, I think, using mobile phone, they connect into internet, and that's the first one. This is exactly the case. So the first presentation will be given by Ihar FILIPOVICH. He is from Belarus State University, and he is third year bachelor's student, and the topic is defense from adversarial attacks on deep neural networks using denoising net. So, you know, recently there is a problem of adversarial attacks, and this is very important problem of safety. But in my view, the problem is underestimated by specialists so far, up to date. And even some of them don't really want to pay attention to this, but it is important to keep everything, all the applications safe. So that's actually the essence of this topic. So Ihar, are you ready?
Yes, I'm ready.
Okay, then please start your presentation, share the screen.
Okay. Okay, do you see my screen?
Don't forget unmute your
Yes.
microphone.
Okay, can I start now?
Yes.
Okay.
So we are listening.
Okay, good morning, dear ladies and gentlemen. My name is Ihar FILIPOVICH, and now I'm going to tell you about the defense from adversarial attacks on deep neural
By the way,
networks.
if there is some, also we are still in time, but still we are waiting for starting of presentation.
No, the presentation already started, so we see your screen. Please proceed.
Okay, now I'd
So
like to tell you
Igor,
about...
we see your presentation, the first slide, but we are not have sound.
So...
Dr. Vassili, actually, so the sound is muted probably just on your computer because everybody actually see the presentation and already hear the voices. So check your computer and check your sound. So Igor, you may proceed probably.
Okay, thank you. So I'd like to tell you about the defense from adversarial attacks on deep neural networks using denoising.
Okay, good.
And first of all, I'd like to remind you what is an adversarial attack and why do we need to defend from them. So the adversarial attack is some change in the initial picture so that it is not visible by a human eye, but our model becomes to predict incorrect results, and that's possible because of the fact that our models are not ideal and there is always a part of space where it makes mistakes, and the goal of the adversarial attack is to define that part of space and to move our image there. So and you can say that these attacks are not real and can be reproduced only on the computers, but here you can see the example of the real world adversarial attack when the turtle was printed and was photographed. So, but from all the angles, it wasn't recognized as a turtle and was recognized as a rifle. So after that, as we saw that these adversarial attacks are possible and can be a real threat for our models, let's move on to the consideration of the different defense types of our models. And the first thing that comes to mind when we think about the adversarial attacks is just to generate that adversarial examples and then add them to our training data sets. So then train our model and we will get the better and more robust model. But here's a trade-off that works only for small data sets, and when we have a large data set, we will need to generate a big amount of data, and that attacks take a lot of time, so we will need abnormally big amount of time, so that's not always possible. That's why people thought and decided that let's generate not all the adversarial attacks, but let's generate some noise that will be similar to the attacks, and that's turned out that Gaussian data augmentation scopes great with that, but also that's obvious that it can't reproduce all the attacks, so that is less effective but much more faster. And the next method is using label smoothing, and label smoothing is a very simple and well-known method which helps us to protect our model from overfitting and different perturbations. And the idea of the label smoothing is just to penalize our model for giving two certain results, so it becomes more robust. And so the next way to protect our model is to use bounded rectified linear unit as a activation function. So that helps us because a lot of model adversarial attacks use gradient explosions to to attack our model. So when we use bounded activation function, we protect it from the gradient explosions, so our model becomes more stable. But here's a trade-off too, because when we use bounded activation function, we are not protected from the damping of the gradient, so it can also be a problem in the future. And the next method of the defense is to use ensembles of models. So it is obvious that if we use one model and attack can trick a single one, but when we use a lot of models of different structures and different types, it is much more complicated for attack to fool it. And the last one method that we will consider in our report is the denoising of the images, and that's the method that we will consider during the whole part of the report. And now let's move on to it. And at the beginning, I'd like to say that denoising can be represented by different ways, but today we will consider only denoising by neural networks. And first of all, I'd like to introduce some notations. And as a clear image, initial image from our dataset, we will notate as X letter. After that, we add some adversarial noise to it, which will denote as a DX with a star, and get the adversarial example with a noise, which will denote as an X with a star. After that, we want to predict some noise, and the predicted noise will be denoted as an DX with a hat, and the predicted clean image will be denoted as an X with a hat. So now we can move on to the simplest models and consider them. And the first idea is just to get some several linear layers or convolutional layers and define our model as a model that predicts from the adversarial image the cleaned one, and use as a loss function just per pixel difference of the clean image and the real one. But that always that model is too simple because the structure of images can be too difficult, and that won't work with a complicated attacks. That's why we can introduce the denoising autoencoder model, the idea of which is simple too. At the beginning, we just use the encoder part neural network into which we pass our image. From that encoder, we obtain the low-dimensional representation of that input in the center. After that, we pass it to the decoder part, inside which we are trying to reconstruct our image, which will be cleaned from the adversarial attack. But that model has a problem too, because in the center we have a bottleneck where we have a lot of losses on the data, because we lose a lot of information about initial image here. And that's why we can modify the model and present the denoising VNet, which fixes this problem by adding skip connections between the encoder part and the decoder part. So on each layer of the backward pass in the decoder, we just concatenate the results from the appropriate layer in the forward pass, and that's that makes us not to lose a lot of information. And the other fix here is that, as I've mentioned before, it is not a good idea to predict the whole image, because it contains a lot of information. But usually the noise that we want to predict is much less intensive. So let's predict that noise, and after that, let's add it to our adversarial image, so we will get the cleaned one without the noise. And now let's consider the structure of the denoising VNet in more details. First of all, we pass our image to some convolutional blocks with convolutions, batch norms, and rectified linear units. And after that, several sequent convolutions goes, and each convolutional layer of 3 convolutions contains 3 convolutions, and the first one always contains a stride equal to 2, and with that we decrease the size of our image so we can get the low dimensional representation. Then after the forward pass, it's our encoder, we go to the backward pass of the encoder. So here we don't need the stride, because we are going to increase the shape of our image. So for that we have, before each convolutional block, we have a fuse unit, which contains a bilinear interpolation function. And also on that fuse unit, we concatenate the results from the appropriate layers on the forward pass. After that all, we have a convolution with a kernel size equal to 1, so we can reduce the channels number to 3, so we get three-dimensional image of noise, which we can subtract from the denoised image. And another thing to discuss that before we've said that using per pixel loss is not a good idea, because really it doesn't matter for us how the image looks like. What is really important for us is that the representation of that image on the last layers of our classifier, because from them we will make the predictions. So the idea is to get that representations and to use them in our loss function. And in this way, we can obtain the high-level representation guided denoiser. And here we have a choice which layer to use to get that representations. And we have several cases. And the best one is just to use the layer before the last, where we obtain the features of our image. So we get the feature guided denoiser. And of course, we can use the last layer where we obtain the logis of our picture, so we get the logis guided denoiser. Moreover, we can say that here we have an example of unsupervised learning, because really it doesn't matter for our models which label has an image. Everything we need is just an image and the attacked one to denoise it. So the unsupervised learning. But of course, if we have labels, we can add them, and we can unite our denoiser with a classifier model. So we will train our denoiser on the classification loss, and so in this way we will obtain the class label guided denoiser. Okay, and that's the end of the theoretical part. Now let's move on to the experiments which we made during our research. And first of all, I'd like to tell some words about the dataset that we used during our experiments, and that was a part of ImageNet dataset with 10 classes. And the model that we used was a fine-tuned efficient net B6, which scores accuracy of 94% on that dataset. And here you can see the training of our model, and here we want to say that you see that the validation curve is always better than the training curve loss, and that happens because of the fact that during our training we've used a lot of augmentations. So that augmentations included Gaussian augmentation too, and Gaussian augmentation was called a type of defense from adversarial attacks. So now we can say that our model is already resistant to that attacks, and that will influence on the future results of our experiments. Okay, and the first thing that we did is just apply that attacks on that dataset. And we see that our model becomes much worse, because we see that accuracy is less than 80%, and on the last stack is even less than 40%. And about the attack that we used during our report was the APGT attack. The next one was the auto attack, which is the ensemble of different attacks. And the last one was the IVGSM attack, which is the strongest one, as you see on the accuracy score. But we should say that that accuracy is the strongest one by the perturbations too, because it makes our image too perturbated, which is even seen by a human eye. But really, it doesn't matter for us, because everything we need here is just to compare our models on different attacks with different strengths. And the next thing that we did is we did some baseline for our model, and as a baseline, we've decided to make adversarial training, and you can see that the quality of that model is better than on the raw model. And for adversarial training, we've used 25,000 generated images and put them onto our data set, but we can see that that amount of data is not enough to get the desired quality, because you see that quality is not enough too, in comparison with 94% of accuracy that was scored on the clear images. That's why we made our high-level guided denoiser. So we see that the result is even better on the than the adversarial training, but also I'd like to add the thing that we didn't have enough time to train that denoiser properly, so it is not fully trained, but already it gives the results better than on the adversarial training. So we can conclude that our denoiser model is obviously better than the adversarial training, and if we train it in a big corpus of data, we can obtain the results that we want. And moreover, as we don't need labels for our data, we can use the unlabeled data, which we can obtain easily. And now I'd like to move on to the conclusions on our report. So during the report, we've described several defense types and how they can help us to protect our models. And the last one was the denoising, and we wanted to describe different denoising models and denoising neural nets. And we've described such denoising nets as pixel-guided denoiser, to auto-encoders, to denoising UNet, and we've come to the high-level representation guided denoiser, and as it is the strongest one. After that, we've moved on to the experiments and shown that the adversarial training is a good baseline, but after that we've showed our high-level representation guided denoiser that scores a better result, so we can say that it's a good model to use to define our classifier. So that's here you can see the references that for our report, and that's all. Thank you for your attention.
Okay, thank you very much. It's a little bit longer than 15 minutes, and we are still in time simply because I saved time before, so I gave 1 minute to you. Okay, thank you very much for your nice presentation. We have a few time for short questions, and next presenter, Dmitry, just prepare yourself. So please, questions. No question. So I've got one. Maybe I missed the point. But have you considered Karolini-Wagner attacks?
No, we didn't consider that attacks. We've considered only those 3 attacks that we presented on the report. That were 3 attacks. One APGD attack, which is the attack of the 2023 year, and auto attack, which is the ensemble of that APGD attack, FAB attack, and a square attack. And the last one was the strongest one, DFGSM, which is also the attack of the latest years.
Okay, thank you very much. Okay, thank you very much for your good presentation. So we need to remember that Igor, perhaps the youngest participant of our conference, and a reasonably mature or student presentation he gave us today. Thank you very much, Igor. Okay, next presentation will be given by Dzmitry KARSHAKEVICH. He's also bachelor students, but 1 year more, is a 4th year of study, and he's also from Belarus State University. And we know him also because we are lecturing on that course with Professor Tuzikov. And the presentation title is Development of Methods for Texture Analysis and Classification of Medical Images based on Deep Learning Methods. Okay. Igor,
Yes.
floor is yours. Please go ahead. Please share the screen.
Okay. Can you see the screen?
Yes.
Yes, everything is okay. Maybe just, yeah, you got it. Thank you.
Okay. Hello, my name is Dmitry, and today I'll tell you a bit about texture analysis, classification of medical images based on deep learning methods. And first of all, my talk will focus on working with histological images as indicated on the slide. And initially, when I started working on this project, the main goal was to develop a neural network feature generator for such histological images in order to then build classifiers or more complex models using these features. And for this reason, this direction will be the main focus of my report. Well, for this work, I used a process dataset from the Chameleon 16 competition that was held in 2016. And this dataset contains 3 classes of images: healthy lymph node tissue, epithelial tissue, and 1 containing metastasis. In total, every class contains 4,200 training images and 1,800 test images for each class. Okay, now we can say that one of the characteristics of histological images is that they are quite homogeneous and are essentially like textures, which suggests us an idea that it is possible to use some feature characteristics, texture features, when working with such histological images. For example, looking at a histological image, we can see that it is very grainy, or vice versa, it's very smooth or uniform. And moreover, it's worth paying attention to it when using some neural network methods, since there are a couple of researchers that say that common neural network architectures that work with images don't take into account some texture features so well. So to do this, consider such a term as co-occurrence matrix, which was proposed by Herlich in 1970. You can see the strict definition on the slide, but intuitively, you can explain that the element ij shows how often pixels with brightnesses I and j can be found next to each other in the image. Okay. Such a matrix can be a pretty good descriptor for images, and there are even some studies that build classifiers from such matrices, but it's not the matrix itself that we're interested in, but some other numerical characteristics that we can calculate from such a matrix. The main application is that it allows us to numerically estimate some texture properties, such as homogeneity or correlation or contrast. Let's look at this with an example. Here I took images from 2 different classes, a healthy lymph node tissue and epithelial tissue, and calculated co-occurrence matrices for them. And the difference between these matrices is immediately obvious. As you can see, epithelial tissue, which contains fewer fine details, has a matrix with values that are more dense and concentrated at the main diagonal, unlike lymphatic tissue. And if we count the homogeneity value from such matrices, we can see that lymphatic tissue has this value almost half that of epithelial tissue. Okay, and then I began the experiment. I calculated a vector of 6 numbers for each image, and these characteristics are shown on the slide with their formulas. And in order to check how much information these features contain, I decreased the dimensionality using the principal component analysis. And it can be seen that the obtained clusters are quite compact, although they overlap each other, of course. And this gives us an idea to train some simple classifiers on these 6 features. And to do this, I used a k-nearest neighbor classifier, logistic regression, and support vector machine. And you can see the results of the experiments. And in general, it's quite an interesting result that a complex histological image is enough to be represented only by 6 numbers to achieve quite good accuracy in 72%, as was achieved by SVM and was almost achieved by logistic regression and k-nearest neighbors. But however, this accuracy is not enough for us, of course. So next, I started experimenting with more powerful approaches. And at this stage, I took the ResNet 15 pre-trained neural network at the basis and fine-tuned it on our sample. And the resulting accuracy was almost 95% on the validation sample, which is a much better result. Okay, now that we have looked at the 2 different approaches, we might be wondering what would happen if we combine them together. And at this point, I concatenated hierarchic texture features with convolutional neural network features, feeding them to different classifiers afterwards. And on the next slide, you can see the summary result for the 3 considered approaches. Okay, now it can be concluded from the results of the experiments that combining neural network methods with classical approaches to texture processing can give quite high results in the classification of biomedical images. At this stage, there are still many unexamined methods that could potentially improve the quality of classification, such as the use of wavelet analysis, for example. So to be continued, and thank you.
Okay, Dmitry, thank you very much for your brief and nevertheless very nice presentation. Please, questions. We have still time. Yeah, we have good enough time for questions in this case. Anyone wants to ask something? Something like, okay, you are working with color images, but how you calculate that hierarchic features, etc.?
Well, I transformed them to grayscale images.
Yes.
When calculating this metric.
Yeah, perhaps people guess it by themselves. Good. Also, to me, it is interesting that so you got with the neural net on the output of convolutional part, you got a feature vector. And I don't remember SNet 50, how many are there, by the way. How long it is, this vector, this case?
2048.
Okay, okay. So and then I also did such kind of experimentation. Then later we will see each other, then I will tell you in details. But have you ever interested about the correlation of this feature table, and what's how it number of have you applied the PCA, because it's redundant? So how have you used PCA to reduce further that's neural net based features down to a much less subset of principal components?
Well, the PCA was used only to visualize these clusters, but the only experiment I did is to calculate the square correlation between these features to see which
they are correlated. They are not, well, principal components, they are not correlated, but original features, this is special long number. When we see to the images, they are reasonably poor, they are homogeneous, etc. So I will never believe there will be 100 principal components out of that 2048. So there should be very few of them, in my view. And then it is interesting how does it works in the for classification. Is it?
Yes, of course.
Yeah. Okay. Maybe someone got some more. Okay, Axel, please.
I would like maybe a short question.
Okay. Alexander, you go ahead. Okay.
I would like to say a short question, if Vassili, if you don't mind.
Yeah. Also, Axel got. Right.
Okay. And
Okay.
Alexander, you go ahead.
Okay. Just to say to Dzmitry KARSHAKEVICH, because Heraldic features is like a well-known characteristics already developed many years ago, and after that there were many developments, further developments of these characteristics used for texture analysis and maybe also processing. Especially Vassili Kovalev is a part of his long experience is based on some generalization of these Heraldic features. Maybe it will be also interesting for us, because you are working together with Vassili, to show how powerful from this point of view is this generalization of these features. So-called generalized covariance matrices. Maybe next time when we see your presentation, maybe, or your diploma work, you also present us, besides Heraldic features, also these features, how powerful they are.
Okay, thank you.
It's my question, and also maybe some proposition to you.
Okay, we'll talk with Vassili about it. Thank you.
Okay, Axel, go ahead.
Yeah, so thanks for your nice presentation. So do you find any evidence whether maybe the ResNet has learned some of the Heraldic features? Of course, we know, like convolutional neural networks in the very first layers, we know that they can learn certain convolutional filters, and if one looks into the trained models, one often finds the network does some calculations like Sobel filters. So for convolutional filters, people have looked into this. Do you find, or could you imagine a way how to examine whether the neural network probably in the first two layers has learned something like the Heraldic features by maybe correlating activations in the first layers with Heraldic features? Do you find any such evidence, or do you have some idea of how you could investigate this?
Well, you say that there are probably already these Heraldic features in neural network features. Well, one way to check it is to, as I already said, for example, to calculate his squared coefficient to see which features correlate with the answer more or which less. Or, for example, we can build a logistic regression based on these features and see which weights are fewer or which are greater. And if logistic regression pays more attention to these Heraldic features, then they are quite important and probably could not be found in the neural network features.
By the way, Dmitry, maybe you missed some point what Axel pointed out, mentioned. So if I understand correctly, Axel, you were talking about the early convolutional layers, which are just something similar to traditional Sobel mask or something like that. So it's not the final features, but the early features.
I mean, yes, probably the Heraldic features, if they somewhere show up in the neural network, probably they will be found rather in the early layers, I would guess.
Yeah. So that's sort of suggestion for your future work, I think. Okay.
Okay, thank you.
Gentlemen, ladies and gentlemen, let's go ahead. Now, so it was two presentations were about images, image analysis and such classification and such things. But the next presentation, which will be given by Stanislau, also presenting Belarus State University here, and he is also fourth-year bachelor student, and he will be talking about text, I suppose. That's perhaps text. Okay, anyway, he will tell about his presentation by himself. And please, Stanislau, if you are ready, then go ahead. So we see with whom you are collaborating in preparing slides. Okay, go ahead, please. Floor is yours.
Okay, do you hear me?
Yes.
Okay, good morning, ladies and gentlemen. My name is Stanislau BELIASAU, and today I'm going to tell you about BERT-based biomedical named entity recognition and normalization task. During my report, firstly, we will discuss the definitions of named entity recognition, named entity normalization tasks. Then we will stop on the BERT model. We will discuss the data set I have used for evaluating the models, and then we'll stop separately on each of the named entity recognition and named entity normalization tasks. So, named entities are meaningful terms or multi-word phrases, and named entity recognition it is a task of locating and classifying named entities in the text into the predefined categories, such as disease names, person names, organizations, and many other categories as would you like. And after the named entities have been recognized, the next step is named entity normalization by mapping recognized mentions to suitable identifiers into the vocabulary. So let's have a look at the picture. Here we can see two biomedical mentions that are yellow, renal failure and decreased renal function. They seem very different, but they both relate or correspond to one concept name, renal insufficiency. So that's the task of named entity normalization. It's necessary to resolve the ambiguity in the biomedical texts. So now let's speak about BERT. Why have I used BERT? Because now it's the most commonly used pre-trained model in modern NLP. It was a real breakthrough in 2018 when the team of Google researchers have presented the model. And since then, practically each NLP model uses BERT in it. And it helps to achieve real good results in biomedical text analysis. So BERT uses a masked language model, and hence it can be used for learning bidirectional representations. And the main difference between BERT and many other language models is that it produces contextually dependent embeddings. So we can store the information about the sentence, about our corpus in each embeddings. So it can be used for getting better representations of our text. And BERT is initialized with a checkpoint of simple BERT, followed by the fine-tuning of this model. On the picture, you can see the process of the pre-training. We have a huge, very huge corpora of biomedical texts, initialized our weights with the BERT model, and then we just using a masked language model to fine-tune the BERT to our biomedical domain. So next we will discuss the data set. For this task, I evaluated near and near models that I will describe below on English NCBI corpus. It covers major biological entity diseases, and it's a golden standard data set of disease and named entity recognition, named entity normalization tasks. It consists of disease mentions mapped to their concept IDs into the predefined medic vocabulary. So let's stop on each of the tasks. Firstly, as we're analyzing text, we have to pre-process the input data. Firstly, we mark each word in sentence using IOB format. Then we tokenize each sentence with BERT tokenizer and preserving text of tokenized words. For example, if you have an input sequence of words like insidious ventilation and corresponding sequence of IOB text, and after applying BERT tokenizer and preserving the text, we have a new sequence of tokens and a new sequence of corresponding IOB text that satisfies the initial input mention. Finally, we have to pathogenized sequences to have equal size to feed it to the BERT. And during training, I used ADAM optimizer, cosine scheduler, and trained the model during 50 epochs. Here you can see the validation and train curves during training the model. As you can see, the loss on validation and train each decreases. So we can finalize that the model was learning and it was good. Now you can see the comparison of model that I have described above and the current state-of-the-art model on named entity recognition biomedical task based on 3 metrics: precision, recall, and F1 score. You can see that I have practically achieved state-of-the-art results by just by doing the simple things that I have previously defined. So let's stop on the named entity normalization task. The goal of the task is to assign to a mention M its a unique concept ID in the target dictionary. And let's get a strict formulation. Given a list of mentions M and set concept of concept IDs C and concept names N from the dictionary. And the task is to map each input mention to a corresponding concept ID through a normalization functions that is just the ID of the concept name with the highest score that I will define a little later. So here you can see the model architecture. It's pretty simple, consists of 3 steps: candidate concept generation, candidate concept ranking, and entity disambiguation. Each of the steps I also will describe a little later. But firstly, I have decided to fine-tune the BERT model onto the NCBI disease domain. So I have just executed an additional step of pre-training with a masked language model. I have just taken the texts from the NCBI disease dataset, split it into the sentences, and randomly masked 15% of tokens, and trained the model to predict the masked word. So now let's discuss the model evaluation steps. The first is pre-processing, next is candidate concept generation, candidate concept ranking, and entity disambiguation. Now let's start on the pre-processing. It includes 4 steps: resolving abbreviations, lowercasing characters, and removing all non-alphanumeric characters, and splitting composite mentions into separate mentions. For example, if we have an initial mention, breast and ovarian cancer, we have to split it into 2 mentions: breast cancer and ovarian cancer. Now, let's get to the model itself. The first step is candidate concept generation, and the goal of this is to construct a list of candidate names from the dictionary, which consists of k possible concept names for the given input mention M. Then we extracting embeddings for mentioning each concept name from the dictionary and counting simple pairwise static BERT scores. This is just cosine similarity or cosine distance between 2 vectors. And then we just retrieve k concepts with the highest scores. The next step of the model is candidate concept ranking. The goal is to get additional scores for each candidate name by fine-tuning the BERT transform binary classification task to ranking task. So for the moment, we have k candidates for the mention M that we have just retrieved from the previous step. And how we're getting additional scores, we just generating all mentioned candidate pairs, getting labels for each pair, where some pair has a label equals to 1 when the IDs of candidate name relate to the IDs of our input mention. And for each pair, we creating such a sequence, applying BERT on it, and taking the final layer of the CLS token that represents the sense of whole the sequence. Then we just apply a linear layer to it. For the classification task, we just map an dimensional vector to 1-dimensional space, applying sigmoid on it to get the probability. And that will be a new score, ranking BERT score for our pair. The next step is entity disambiguation. The goal is to re-rank the list of k candidate names according to the final ranking scores. The final scores is just simply the sum of 2 previously defined scores. And the corresponding concept ID for our initial mention is just the ID of the concept name or candidate name with the highest final score. For evaluation, I used two metrics to control the quality of the model. The first is accuracy 1, and the second is accuracy 5. The accuracy with index k means the percentage of mentions in the corpus which contains the correct concept ID within the top k retrieved candidates. Now you can see the results and the comparison of the models that I have described above and the current state-of-the-art model on the named entity normalization task on the two metrics that I have defined. So let's visualize how the algorithm works. We have an input mention, inherited cancel syndrome. Then we just getting top k candidate with the highest static BERT scores. This is just the cosine similarity between mention embedding and concept name embedding. Then we just getting ranking based scores with our calibrated classifier, summing up the scores and finally rank the list by that final score. And then we just choosing the candidate with the highest final score. For us is cancer syndrome hereditary, and it will be the normalized concept for our initial mention inherited cancer syndrome. So let's get to the conclusions. Today we have discussed named entity recognition, named entity normalization definitions. We tried to understand why named entity normalization is important for us. I described the BERT model, the data set that was used for named entity recognition, named entity normalization task. Also, we described each of the tasks and discussed the results that we have got. So here are some references, and that's all. Thank you for your attention.
Okay, thank you very much. We are still in time. So we have time for our questions, please. Go ahead with questions. Who want to ask?
Okay, maybe I would like to ask Vassili a question.
Yes, please.
Or a couple of questions. Thank you very much, Stanislav, for your presentation. In fact, we and myself, I'm not working with natural language processing, but I would like to just to ask you a couple of questions because
Okay.
I missed several details in your presentation. To say the truth, also even your presentation formally was very good, and you presented quite careful. Not everything was clear for people which are working outside the topic you are working now. Okay, so when speaking about this BERT model, you showed it as a black box in your presentation, but can you say a couple of words about it, because about this black box, or not black, yellow box model, because it's in some literature. I've met this model, and maybe you just say a couple of words how it is, what is inside this model.
Okay, BERT model just uses a thing called attention. It just we have an input embeddings for each token that comes to the input of the model. Then we just taking the embeddings of some token and getting the information about all the tokens in the sentence. I don't know, using simple dot product of all cosine similarity, we are getting new scores. Then we get a new vector representation that consists of the scores, which are just the dot products of our input embeddings and the embeddings of each token of the sentence. And then we are applying sigmoid on the new gut vector, getting the probabilities, and this way we understand which tokens in the sentence are the best to describe our initial token. And we have several stacked layers like that, several stacked attentions. And during passing all that layer, our BERT understands the context and the sense of the text that we give him as an input. And that's why it's so powerful thing.
And BioBERT this model. It's developed by you, or you've taken also from some literature.
Yes, I have just taken a pre-trained BioBERT models. I have taken a pre-trained BioBERT model that was trained on very huge biomedical corpuses. You can see here 4.5 billion words and 5 billion words. It was trained, I don't know, during some weeks. I know it took 21 days to train the model, but now it's in open source, and every researcher can take it and use in his purposes.
And when you're speaking about this corpora where you did pre-training, about their capacity of them, when you have your initial inputs, you have some like not one word but several semantically linked words. How this now you can use this and you have to deal with not one word but several words, and how it is like this semantic sense between these words is what is his role in this model?
Okay, I described it. I have, as I told, I executed an additional step of pre-training. I took the texts, the abstracts of the PubMed articles that are given in the NCBI disease corpus, and fine-tuned the BERT on them on the masked language model task. I have just randomly masked 15% of tokens and learned the BERT to predict the masked words. So that way it has learned the semantical specialties of the data of the NCBI disease corpus, and that increased the results that they've got before the fine-tuning.
But what is like the main topic of this your developments when you have, for example, your input ovarian cancer? So just and you are now analyzing this database of for example scientific publications from devoted to ovarian cancer. So what is like the main output? You just rank the articles on the score of which show the relevance to these ovarian
I don't rank
input, or what, or you do more than only this?
No, I'm not ranking the articles. I'm ranking the embeddings of the mentions of the disease names, not articles themselves. So after fine-tuning the BERT, the BERT understands the relations between word units in the text. It learns these relations. And then we just apply the BERT on the sequences of words which represent one mention, disease name. And it creates a good contextual dependent embeddings of the word of the mention, which we can then rank with the embeddings of other input mentions. So the main task of my research is to resolve the ambiguities in the biomedical texts when different people use synonyms or different words to describe a single entity.
Yeah, but as a user, for example, myself, I'm interested. You are a developer, for example, and I'm user. I'm interested, for example, to to having ovarian cancer and maybe some other things like diagnostic on ovarian cancer based on histological images, to have such an input and to get more relevant, for example, publications on this subject. Where is your place in this, like in solving this main goal?
I think it's a little different task. Because the main task, firstly, is normalization of the string and getting, for example, we have an input article, I don't know, that describes, as you told, ovarian cancer. And during this article, we process the text in it. And we want to get the parts of the text where our ovarian cancer being discussed. So it's used, for example, we have different parts of the text where different synonyms are used for the ovarian cancer. And with my tool, we firstly normalize each mention to ovarian cancer normalized concept. And then we just can simply understand where in text we can meet the information about the mention you want to know.
So you just point the most important relevant parts of some documents to this input.
Yes.
Okay, thank you very much.
Thank you.
Okay, we have just 2 minutes for another question.
Yeah, I have a question. Is there any difference between BERT and vanilla BERT? No, except the training data set.
Please repeat your question.
Is there any difference between BERT and vanilla BERT?
Vanilla BERT. Yes, of course, I have just reminded. The BERT uses a very huge corpora of biomedical texts to fine-tune the initial BERT model. So it learns absolutely another semantic dependencies in the text. But BERT is a very good baseline for this task.
Okay, thank you. May I just ask you a question and you say yes or no, because we have no time. So have you seen in this domain the use of graph neural networks for text analysis? Because it's sometimes the meaning of text represented by graphs. Yes or no? Have you seen such works?
No, I haven't met the usage of graph neural networks in the NLP, but I think I will read about it a little later.
Okay, thank you very much. Okay,
Thank you.
Thank you very much for your presentation. It was very detailed and very densely populated by different terminology, etc., etc. Thank you very much. So the next presentation will be given by Kirill Yematsinov. He's also from Belarus State University, but comparing to previous students, he is master student and he is 5th year or 6th year student. That means the 2nd year master student. And his topic is self-supervised learning in medical imaging. Please, Kirill, go ahead.
Yeah, hey, again, good morning, everyone. Vassili Alexeyevich, thank you for this opportunity to listen and share some insights. The presentations before, they were very interesting, some valuable information. So yeah, thanks everyone. My presentation is more like overview of an area where I'm currently doing my master's degree. So yeah, I guess it's not that detailed, but just give me a second to share my screen. Can you see my screen now?
Yes.
And can you see the slides moving now from the title slide to outline, or no?
No.
Okay. Just a second then. Yeah, now everything is okay, I think. Okay, to start, I want to share some idea. I'm convinced that a lot of researchers, and even specifically researchers here, have encountered the small data set curse. When you just can't train your model well on an available amount of samples, especially when it approach or architecture where you can't use simple pre-train and something like that. Yeah, like lack of labeled data in general is one of the most challenging problem in some applications of ML. We all know that with the most sophisticated architectures, but without sufficient data set, we can't solve any task, and it's obvious. Today, I'll speak about one of the approaches that help us to deal with this lack of data problem. The outline of my presentation is I will describe in general self-supervised approach, yeah, and like just how to use it and what is it. I'll mention specific examples of self-supervised tasks. Yeah, they're grouped, and they grouped here, and applications in medical imaging, and we will answer the question how self-supervised learning can help us in our routine work, help our net to learn something better, and so on. Speaking about self-supervised approach or self-supervised task in general, as I said, usually we can use it in the situations when we don't have enough data. In fully self-supervised approach, idea is basically to get good feature extractor on unlabeled data, as it is. But of course, in real-world setup, we still need some labeled data, at least for validation, and usually we can use small amounts of it for fine-tuning our self-supervised trained network. So yeah, this approach is usually called semi-supervised. Speaking about, it's like the 0 point, yeah, like we need to understand which setup is useful for us. Speaking about next point, it's invention of self-supervised task or choosing. If we are just not doing research, but rather trying to improve our model in production, for example. The main question here is how to get good feature extractor without any labels. The trick is to use labels which are naturally aligned with our data. And based on them, we can formulate some artificial or self-supervised or pretext task and use classical self-supervised approach to solve it. Yeah, model is just trained to solve this task in supervised fashion with supervised loss function. And feature maps of this model trained for solving this artificial task can be used as image representations or model. This model, like its weights, can be used for fine-tuning. Yeah, and want to point out that, of course, improving the quality or metrics on our self-supervised task is not the main idea here. Of course, it's important to solve well this self-supervised task, but the main outcome for us are feature maps that we can use later. Now I want to discuss some approaches previously published. One of the most simple but effective and like understandable maybe ideas is rotation network. The self-supervised task here is just use input image, rotate it by some degrees here, and the model is trained to predict which rotation has been applied, like just for class classification problem. Yeah, and authors of the paper, they claimed that in order to identify same image with different rotations, the model has to learn or recognize high-level object parts, such as heads, noses of birds, yeah, for this specifically data set, and relative positions of this part. Yeah, I will share the metrics a little bit later when we discuss some other approaches. Another self-supervised task is context CNN, self-supervised neural net, let's call it this way. The idea is just to predict relative position between two random patches from one image. We just sample the first patch without any reference to image content. Consider that the first patch is placed in the middle of grid, and the second patch is sampled from its neighborhood. Yeah, they also add some noises to avoid trivial solutions. You can see that this is not just grid, but we add some gaps between patches, small jitters, maybe downsample some patches, and something like this. And the model is trained to predict which one of the 8 neighboring locations the second patch is selected from. Yeah. The idea, jigsaw puzzle, I think we all see something like this. The idea is pretty simple to previous, pretty similar to previous task, but we just predict in some the array of numbers, yeah, the permutation of patches. Colorization, also really simple idea, just to take colorized images, make them grayscaled, and try to teach neural network to colorize them. Yeah, speaking about benchmarks of these approaches, RotNet, of course, it's not ours, not mine, but I just take this table from their papers. They actually reported that, speaking about detection task, it's maybe the main interesting fact, that they got results just using their pretext tasks, and then train one-liner linear layer based on features got from these pretext tasks. They just really close to supervised approaches. Yeah. ImageNet also benchmark, also quite close. Speaking about another way of how to solve this problem, how to make self-supervised tasks, we can remember augmentations. The idea here is another idea is really simple, to use hard augmentations, minimize the distance between different augmented views, and maximize the distance between these views and other objects in the data set. So yeah, basically just described this idea. Of course, it has some degree of freedom. We can choose a specific class function, etc. And speaking about this approach, swapping assignment between views, They also they compute code from an augmented version of image and tries to predict this code using another augmented version of the same image. So it's like pseudo labels. Yeah, another way is deep cluster. Deep cluster just iteratively clusters features with k-means and use clusters as pseudo labels again. This idea with pseudo labels is quite popular and really useful in this field. Actually, speaking about my own research, my own master's thesis, yeah, I'm doing something like this, but my pseudo labels they are coming from handcrafted features, yeah, like LBP, for example, or heraldic features that was mentioned before. Yeah, and I'm trying to pre-train network using the predictions of these pseudo labels. Yeah, also wanted to mention that we can even GANs and VIE, we can consider them as self-supervised approaches too. In autoencoders, self-supervised task is to reconstruct a match, and we can use that vector as representation. And in GAN, we can use just layers of discriminator. Actually, one interesting fact is the original paper name of DCGAN paper. It was not something like deep convolutional GAN for creating images. It was unsupervised representation learning with deep convolutional GAN. Yeah. Speaking about, of course, we can use these approaches in medical domain, but in medical domain, we can also use some domain-specific features. For example, speaking about histopathologic images, usually we can use different scale. Yeah, we can just select a random point on image and random magnification of image, and we are trying to predict the order in which we choose the magnification. This is one of the pretext tasks, and they got a pretty, I can say cool, maybe, result, boosted metrics in this task using this strategy as pre-train. Yeah, another way, another idea that we can use here is the semantic of anatomical patterns. Yeah, because we just can see that medical images, they are usually well aligned in a spatial dimension. Therefore, if we select the random spatial position on some reference image, the same spatial position on the other image of the same data set usually will present very close semantic information about the imaging object. So we can just make crops of the same points and try to classify them. Yeah, and speaking about how self-supervised learning can help us in general case, like I mentioned some specific task, but can we use it like for our own research? Well, just a novel paper of Google research team, they created a simple framework just based on approaches that I mentioned before, and tested it on a lot of data sets. And I think the mean boost of metrics that they got was around 5%, if I remember correctly, when we are using this pre-train, compared to just simple pre-train from general data set like ImageNet or something like this. So yeah, you are free to test some of these approaches, and to maybe they will give you metrics improvement. Basically, that's it. That's my presentation. Thank you.
Thank
If
you
you
very
have any
much.
questions, you can contact me by email or just ask.
Just ask right now. So we have 4 minutes still. That's good. So please, questions.
I would like to ask Vassili.
Not very long.
Thank you. Thank you very much, Kirill. Very good presentation. I like it very much. Thank you. I would like to ask you about this like medical part of your investigation. So it's you're working with real customers, or just it's like you are interested in this subject, or you have some contacts with medical people, and the task is coming from them.
Yes, thank you for your question. Currently, I just testing these approaches on data sets that are publicly available, and specifically my approaches, yeah, where I'm making pretext task using classical handcrafted features like LBP and others. Just general available data sets, but yeah, answering your question,
So
I
you
don't have.
No, you do not have. You do not have contacts with medical people in our country, or maybe somewhere abroad.
I have some contacts, but they are like the field and maybe the approaches, they're a little bit different that we are using in our work. And also, of course, I have contacts with Vassili Alexeyevich. He is not like maybe like you said from medical people, but he has a lot of contacts. And
so but you told that you use this public available data, not the data available from special, for example, hospital in here.
Currently
Currently
only public available data sets. Yeah, but maybe later yeah,
Well,
I can test the approaches on other.
Okay, thank you very much.
I just want to give some information on that point. That very recently, I just got data set from our Minsk City Oncology Hospital, and this is a huge amount of data. That's whole slide images, and they are more than 0.5 terabyte of the images like you see on this slide. And there are a lot of different tasks, a lot of different problems on that. And there is a person, Professor Friedman, who is happy to consult, to ask the questions, etc., who is working in that. And he is head pathologist of this hospital. Okay, we will see. Okay, good. Now we are going ahead. I think, yeah, we are exactly in time. And
okay. Thank you for attention. Just wanted to share some point just fast.
yeah.
Actually, this pretext task, this self-supervised task, I think the researchers, they made it based on like assumption or ideas how real doctors are working when they're analyzing these histopathology images. Yeah, because of course they're using different resolution and different magnification to see some useful info on the images. So yeah, this working together on the field is really useful here.
Okay, thank you. Let us go ahead. Next presentation will. So now we are going to the top educational level, which is PhD study. And the first presentation will be on this category of students will be given by Aliaksei KOLESAU. And he represent here Vilnius Technical University, Lithuania. And his title of his presentation is Machine Learning Applications in Voice Activation Systems. Okay.
Thank you very much. Do you hear me?
Yeah.
Okay. Thank you very much for invitation. My name is Aliaksei KOLESAU. Actually, I got my master's degree in Belarusian State University, but as you rightfully say, I'm PhD student in Vilnius Technical University now. My supervisor is Dr. Dzmitry KARSHAKEVICH, and today I want to tell you about my research titled Machine Learning Application in Voice Activation Systems. Let's start from the motivation of the research. Nowadays, more and more products use a voice interface for user interaction. Voice assistants in mobile phones, smart home devices, ATMs, cars, to name a few. It's a fast and natural way for humans. But several problems arise with this approach. Let's say you have a coffee machine with a voice command support. If you push a button on it, then it's safe to assume that you want to give some command to the machine. But if you speak near it, the speech can be directed to someone or something else with very high probability. The coffee machine must discriminate between these two situations, which is quite difficult in practice. Furthermore, in that case, you need to analyze the whole audio stream, which is captured by the machine's microphone, which requires a lot of computational resource and is concerning from the privacy perspectives. The product maker can always make a physical or virtual button to start a voice conversation to rectify these problems, but it defeats a part of purpose of voice interface. That's why many products use a special predefined voice command or key phrase to start a voice interaction. For example, Android mobile phones use the phrase "OK Google," and Apple uses "Hey Siri." In order to build a voice activation system, one might use keyword spotting technology. Keyword spotting is a problem of detecting a predefined keyword or key phrase in audio stream. My research concerns keyword spotting models or keyword spotters. A high-quality keyword spotter must comply with relatively high standards. It needs to have high detection scores, both recall and precision. It must work with low latency, but mustn't consume a lot of resources at the same time, and must cope with the intrinsic complexity of speech processing. The speech has a lot of variability and often is corrupted by noise. As we found in our systematic literature review on the keyword spotters, the vast majority of modern systems are built in the same fashion, but with different parts, of course. First of all, the key phrase is split into some parts, which we call acoustic units. The easiest way is to use letters, but for most languages, there are many problems with this approach. Some letters doesn't make a phone, some letters can make several phones, and some can make different phones in different positions. That's why the most popular way is to use phonemes, and another popular way is to use the whole words. After that, the system works as follows. Audio stream is segmented in the possibly overlapped parts, which are called frames. Typical duration of frame is 20 milliseconds. Then some transformations are applied to each frame to extract as much signal as possible and omit as much noise as possible. This is acoustic feature extraction pipeline. Then some computational model is used to get the probability of the event that given acoustic unit is pronounced at the given frame. This part is called acoustic model, and it's neural network most of the times. Finally, the computed probabilities are analyzed, and the decision rule is applied in order to make the activation or not. This part we call a decoding model. I started my research with completing a systematic literature review on the topic, and there are several results from the work, and the main ones are presented on this slide. After analyzing all the studied sources according to the proposed typical structure, we found that almost all works are focused on improving, tweaking, changing the neural network as acoustic model part of the system. It's quite reasonable because it's often the heaviest and the most profitable part of systems in the terms of detection quality. Also, deep learning research is a very popular topic. Also, we found that there are very few papers that work with languages other than English. It's understandable because all main labeled datasets are in English, including datasets for keyword spotting, such as Google Speech Commands dataset, which is the most popular one for keyword spotting. Still, we decided that it would be interesting to focus our research in the opposite directions. So the main question I was trying to answer in my PhD thesis is how to improve the detection quality with parts other than acoustic model, and how to build better keyword spotters for low resource datasets. Our main and strongest results are for the second question, so not to waste our time, I'll speak only about the research on that topic. As before, I'll start from motivation. As I said before, modern keyword spotters are built with machine learning methods, specifically deep learning. Deep learning is a powerful tool, but often requires a lot of training data, as it was said in the previous presentation. For example, it was quite typical to use hundreds of thousands samples with keyword for training in 2014, and nowadays it's okay to use millions. Of course, it is feasible for international corporations for English language, but it's too expensive for research and for low-resource languages such as Lithuanian or Belarusian. On the other hand, sometimes it's necessary to build a voice activation system on the low-resource dataset. For example, when product wants to customize the user experience by allowing to specify the key phrase. One of the popular examples would be a keyword search in audio recordings of medical protocols. In that case, the product can ask user to repeat, for example, disease name, for example, like 5 times, but of course not 1,000,000 times. Another example would be a product in Lithuanian where we don't have big labeled datasets. Shortly, the goal of my research was to improve the quality of keyword spotter on low resource datasets, comparing to standard ways to build a keyword spotter. We started from collecting and publishing Lithuanian dataset for keyword spotting. We followed the procedure of collecting Google Speech Commands dataset in English. So we asked 28 volunteers to record their pronunciation of 20 voice commands in Lithuanian on mobile phones. Then we carefully processed the records and got the samples for each command. We also collected 292 no-speech records to use them as a background noise for improving the detection quality. We investigated several ways to improve machine learning model on a small data set for keyword spotting. Briefly, the first approach is to change feature extraction pipeline. Machine learning is a powerful tool to extract decision rules from the data, but if data set is small, there won't be enough statistic to extract good rules. On the other hand, we can compute such acoustic features that we a priori believe would be useful for the keyword spotting, so machine learning task will be easier. The downside of that method is that we lose some information about signal, so if our belief is not true, then we can make the situation even worse. That's why with big datasets we use quite simple features. The second approach is to pre-train model or some task where we have enough data. After that, we take the model parameters and fine-tune them on the target task. If the pre-training and target task are close, then the resulting quality will be higher. Finally, we can change the way we train model, which can be useful when the dataset is small. Let's talk about the methods we used. The first method is about extraction of useful acoustic features in a supervised manner. The idea is that there are a lot of unlabeled data and we can use them in order to improve the quality of our model. The method of how to extract useful information about speech is to transform the raw audio data into feature vectors that have a lot of information about neighboring frames. This works because the speech is highly contextual. If I skip few letters in the whole sentence, they almost always can be restored from the context. The same works for audio. The exact optimization problem is quite complex to fit on the slide. You can consult with papers. After we train such extractor on any audio with speech, for example, we use the extractor trained on YouTube videos. We can use the extracted features instead of the usual spectrogram or log-mail filter banks and build a typical keyword spotter on this. Facebook AI Research Lab proposed such method to improve the quality of automatic speech recognition for low resource languages. To the best of our knowledge, we were the first to adopt this method to the keyword spotting. The next method is not ours. It's a very standard way to get the model on the new task without a big labeled data set, not only for keyword spotting, but for any machine learning task. The idea is to train the task, the same task, but on another domain. In our case, we would be training a keyword spotting on the big English dataset, Google speech commands, for example, which is around 1,000 times bigger than our target Lithuanian dataset. Then we remove the last layer of the neural network, initialize it for the task of Lithuanian keyword spotting, and uptrain on our limited dataset. So this approach was our baseline. The next method is not ours. The next method is called exemplar pre-training. That methods come from the computer vision and is very popular there. First, we need to get a big unlabeled dataset, then extract random patches from it. You can see on this slide some patches extracted from four computer vision tasks. In keyword spotting tasks, they can be a random segments of audio or even better random recordings of words. After that, we apply some augmentation to each patch independently. For example, you can see the transformed images of a deer from the last row of patches. This transformation must change the image, but mustn't change the original idea. In our case, that can be speeding up or slowing down the audio, adding background noise, and so on. Finally, we pre-train the model on the task of classification. We give the model a transformed image and ask to identify the original patch. Note that in that way, we are getting a labeled dataset from the unlabeled one. The quality of pre-training methods depends on how rich was the choice of patches and how rich are the transformation. After we finish pre-training, we do the same thing as the previous slide. We remove the last layer, initialize it randomly for Lithuanian task, and uptrain. To the best of our knowledge, we are the first who applied example pre-training to the keyword spotting. So this method is one of the methods that can be used in the list of the previous presentation on self-supervised methods in image processing. Finally, I move to, not finally, but I move to the self-training. Specifically, I used iterative pseudo-labeling. The idea is to bootstrap the model on the given small data set. After that, we use it to label big unlabeled data set. We accept that these labels can be of not very high quality because we trained our model only on small data set. After that, we corrupt this big data set with augmentation and retrain the model on this bigger data set. We can repeat these steps several times. Such self-training should work because each time our model tries to solve a more challenging task, it tries to work as good as the previous model, but the previous model worked on clean data and the new model works on corrupted augmented data. This method works very well for automatic speech recognition, and we try to apply it for the keyword spotting. We use a big unlabeled data set, around 200 hours of Lithuanian lectures without transcription as big unlabeled data set. And finally, the last method we proposed is to train the model on two languages simultaneously. One small target language and one big dataset, for example, English. After the model is trained, we remove the classification of English acoustic units. In our experiments, we found that it's critically important to rebalance dataset, so the model won't simply discard Lithuanian samples because it's not worth to learn it if there are too many English samples. So this is a table that I work on for the last 2 years. On the first row, you can see the results of baseline standard method of training. We took the neural network from the best paper of Interspeech 2019 conference, reproduced its results on big English dataset, and applied the same training to the small Lithuanian dataset. You can see the results on the first row of the table. We report the accuracy of classification. Typically for keyword spotting, false alarm rate, false reject rate are reported. They are also computed in the paper, but the relative results are the same, and it's easier to think in terms of accuracy. Then you see both results where the investigated methods were better than the baseline for the according neural network architecture. As you can see, all the methods have some success, while joint training achieves the best results overall. In short, the use of VAP2VEC and joint training should be the go-to method for the training on small datasets. we know that our proposed methods work better than fine-tuning, which is standard baseline method to improve the results on small dataset. The results of exemplar pre-training are limited because we are not able to get good enough augmentations that mimic different speakers and acoustic conditions. As for self-training, we hypothesized that the Lithuanian lectures dataset was too out of domain for our target dataset to efficiently capture learned features. We reproduced the experiments on English and Russian dataset by using only a fraction of training data and get very similar results. So to conclude, the main results of my research are the typical structure of keyword spotter was proposed, the Lithuanian dataset was collected, and several methods were proposed to improve the detection quality of keyword spotters trained on small datasets. Here's a list of my publication in the reviewed scientific journals on the topic of the thesis. 3 of them are in the Web of Science journals, Systematic Literature Review, and 2 papers on keyword spotters for low resource datasets. Here my other publication on the topic of dissertation, and so these are my other scientific activities. That is all for me. Do you have any questions?
Okay, thank you very much indeed for your nice presentation. Please, questions.
Hey, Alexei, thank you very much for your presentation. I would like to ask you, so you tried already with at least 2 languages, English and Lithuanian. Is there any difference in the quality of your results for these 2 languages? Or the quality is the same for finding these activation points?
So thank you for the question. There are different experiments that we made on that point. So for European languages, such as Lithuanian, Russian, English, and so on, the relative results of the methods are practically the same. So the joint training is the best, and WAF2VEC is also works good. But in absolute values of accuracy, there are some fluctuations, but I think it's not because of the language, but because of the specific commands that we try to classify. So some commands like if you have a long command with many syllables, like OK Google, it's easier to classify than some short word, for example, stop. So I do believe that the difference not because of the language itself, but because of the specific commands to choose. But on the other hand, we try to apply several methods to not European languages, for Chinese, for some Indian dialects, and so the results are not easily explained, I put it this way, and for African languages, of course. So they are different from our, and it's a very rich topic to research, but it's out of scope of my thesis.
Okay, I was just interested in voice activation systems, not using any keywords, special keywords, but just voice, because usually people, native people and also not native speaking people, they speak variously, especially in this intonation, and it should be also important where to activate this pause or something like this. Have you tried also this, tested this difference between native people speaking and just foreigners?
Actually, no, it was out of scope. We haven't tried, but it's interesting way to proceed, of course.
Thank you.
Okay, thank you.
Some more questions, please.
Can I ask a question?
Yes, please.
Sure.
Yes, thank you for nice presentation, Alexei. Can you explain the part where you, as far as I understood, you adapted example CNN strategy from image domain to text domain? Can you explain your strategy a little more detailed? Because as far as I remember, in exemplar CNN, they're using some hard augmentations of the data, and in text domain, I think the data augmentations, they're quite different comparing to image domain, and I'm not really an expert in this field, so it's quite interesting.
Okay, thank you for the question. I want to separate two things. So example, pre-training is independent from CNN. So CNN is like a neural network architecture, and example pre-training is a way to pre-train, so a way to formulate a task. As you rightly said, it comes from image processing, and there are several augmentations, as you can see on the bottom of the slide, like color changing, rotating, and clipping, and so on. So in our task, I wanted to say that it's not text task, it's audio task. Our voice keyword spotting takes audio as input, and output is was there activation, was there keyword in that audio or not. So we do need to augment the audio. As I said during this slide, the augmentation for audio are simple. You can speed up the audio, you can slow down, you can add a background noise, either synthetic noise such as white noise or pink noise or something like that, or you can add some real world noise. For example, you can, as we did, we have recordings of like water running from the sink. We have recordings of some noise from cars and so on, and we can just add them to the source audio to augment it.
Mm-hmm. Thank you very much.
Thank you for the question.
Sorry, maybe last short question. Recently, I tested Microsoft facilities when you just speak into, or you open the Word file and then you speak in and it's automatically recognized and type in the text. And but occasionally in the room there were other people, they also were talking about something. And of course the voices are different and the intensity of voices different and topics are different, but it's still put all together. So I got some mesh of, I don't know, of different words which are typed. So do you know, just yes or no, do you know some works which are trying to separate different speeches which are simultaneously produced by different people?
Yes, of course, there are a big area of research. It's out of scope of my research, but there are a lot of works to separate different speakers and separate the speech that is directed to the computer or something you say and is not directed to the computer. So there are a lot of research going that way.
So it's not just identification of speaker, this is something more complicated.
Yeah. So, yeah, it's like segmentation of speech where you can select the main speaker that you want to recognize or which speech you want to process, and segmenting out the speech that is not directed when you talk it. And of course there is dearization when you want to recognize all the speech, and for each word you want to have a label who spoke that word. So there are different ways to pose a problem, and there are different research for each of the problems, for each of the statements. Okay.
So my guess is that it's just on the research stage, because Microsoft, this service doesn't work properly at all.
Yeah, you're right. Thank you very much.
Thank you for your presentation. Now we are going further to the next presentation, and next presentation will be given by Vivian BRANDENBURG from Ruhr University Bochum from Germany. She is also a PhD student. and the presentation title is inverse folding based pre-training for the reliable identification of intrinsic transcription terminators. Please, Vivian, go ahead.
Yes, thank you. And yeah, good morning or afternoon, depending on your time zone. Thank you very much for the organizers for giving me this opportunity to present my work here. And I know the title is quite a mouthful, so thank you for taking that as well. Yes, I'm working on inverse folding based pre-training for the reliable identification of intrinsic transcription terminators. And now you might wonder what an intrinsic transcription terminator actually is. It is an RNA element, and an RNA is basically a word built of 4 letters. The letters are C, G, U, and A, which in real life stand for threonine, guanine, uracil, and adenine. And so in the age of high throughput sequencing, we know a lot of RNA sequences. But these RNA sequences actually in the cell do form secondary structures following the base pairing rules that the canonical base pairs are CG pairs and UA pairs, and there are some non-canonical base pairs, which, for example, is the wobble base pair UG. And following these base pairing rule, the sequence does form a secondary structure, which might look like this. We have some base pairs here, and some single-stranded regions here, and some double-stranded regions is that. And this example here is a very simple secondary structure, and it is called an hairpin loop. And now the secondary structures in biology do play a very important role because they are involved in many regulatory processes in the cell. And although we have a lot of sequences of RNAs, the deciphering of the actual secondary structure in an experimental way is very complicated and often very time-consuming. And thus, we often have the sequence, but the structure is unknown, although it is very important. And thus, there exists many or some algorithmic methods to predict the structure, and the normal way to go is to find the most stable structure of all possible secondary structures. And for that, there are some experimentally validated base stability pairs. And the most stable pair is the CG pair, and the less stable pairs are the non-canonical base pairs like the wobble base pairs. So as I said, an intrinsic transcription terminator is an RNA element, and you can find it at the end of a nascent transcript. It contains a sequence motif and a structure motif, and the sequence motif is built by an A-rich region and a U-rich region, also called the A-tail and the U-tail. And the structure motif is such a simple hairpin, as I already showed you. So this intrinsic transcription terminator now forms during the transcription process. And when the hairpin forms, the RNA polymerase pauses. And because of the weak pairing between the U-tail and the DNA here, in this moment, this pause gives the chance for the RNA to escape. And thus the process is terminated because simply this whole complex is disrupted. So there are 2 major data sets about experimentally validated terminators, and they come from the 2 bacteria, Bacillus subtilis and Escherichia coli. And we have in these 2 studies together, we have about 1,000 terminators. And we now use those 1,000 terminators to train a neural network. And as you all know, neural networks are a quite data-hungry method, and thus 1,000 terminators or 1,000 data points can be considered a quite limited data availability. And to overcome this limited data availability, we introduce an inverse folding data set, which is an additional data set which comes with the same secondary structure as a terminator, but with a different sequence. And we gained this data set with inverse fold from the Vienna RNA library package. For this, we took the structure of a terminator or of the terminators and random sequences and mutated those random sequences until they featured the same structure as the terminator. And we now use this inverse folded data set to pre-train our neural network first and retrained it then with the terminators. The neural network we used for that was CNN, and we encoded our input data with in a matrix in which we encoded the possible base pairings in the RNA. And base pairings with a high stability had a high value, and base pairs with a low stability, like this wobble base pair here, had a low value. So we had two models. One was only trained with the terminator data itself, and the other one was trained with, additionally pre-trained with the inverse folded data. So this is the performance of my test data set, and we have we see that both models perform quite equally, and in general, the specificity of the models is higher than their sensitivity. And we use the same test data set to find terminators using the method Arnold. And Arnold is a more classical approach to terminator detection, which is based on mainly on a motive finder, and this is combined with an algorithmic structure prediction approach. So to test the performance in a more real-life task, we also scanned the whole genome of Escherichia coli for terminators with our trained model and as well with Arnold. And here we can see quite a difference. Although Arnold already performed quite well, both our models outperformed Arnold, and also the pre-trained model did outperform the non-pre-trained model. So now we wanted to know which of the sections of a terminator has the highest input on our model. So for this, we introduced an experiment in which we introduced single nucleotide mutations into the different sections of a terminator. So the different sections of a terminator are the padding on the left and right side, for which I used the genomic context of the terminator, the A and the U tail, the stem on the left and right side, and the loop itself. And these are the results. And you might see that the impact of the stem rises when the model is pre-trained, and at the same time, the impact of the A and U tail decreases. So one possible interpretation is that the structure gains more influence on the model, while the sequence motifs lose a little bit of their influence. But of course, this might also be due to sequence motifs which can be found in the stem. And thus we wanted to know if our hypothesis is true, and introduced a second experiment. And this time we introduced mutations on both sides of a base pair in a way that disrupted the base pair. And we did that for one base pair, and then an increasing number of base pairs. And these are the results for that. So if in fact the stem stability has an influence on the model output should drop with the disrupting base pairs. And in fact, it does that for both of the models. And we can see for the non-pre-trained model that here we have an influence of the stem stability already. But for the pre-trained model, this is significantly higher influence. And we also had another control experiment in which we did mutate both sides of the stem, but in a way that preserved the pairing. And here you see that, in fact, this doesn't lead to such a drop, and thus we can conclude that actually the stem stability has the highest impact. So to see if this is a principle and a technique which we can also transfer to other RNA families, we took another class, which is the tRNA. You can see this is an RNA which is not only longer, but also forms a more complex secondary structure. And we did repeat this experiment and in fact found the same thing. So the pre-trained model again did react more sensitive towards changes in the structure stability. So I hope that in the last 10 minutes, I convinced you of the following. The inverse folding-based pre-training did improve the detection of the intrinsic transcription terminators in general. Okay. Yeah. It enhances the learning of the RNA structure, which you can see here, and it is applicable to other RNA families as shown with the tRNAs. And I hope that in the future it can be used to at least partially overcome the limited data availability in other RNA families. So with this, I want to thank the organizers of the conference again, and I want to thank you for your attention, and I'm happy to answer your questions.
Okay, Vivian, thank you very much for your nice presentation, which is well done. So please, questions.
I have one question. Thank you very much for presentation. I would like to ask you concerning this combination of nucleotides, RNA nucleotides, which you provided at the beginning of your presentation as this terminator for secondary RNA structure. Is it like 100% confirm that if we have such a combination, then we have a secondary structure element in RNA, or sometimes it's not like this?
You mean if these pairs always can be found in a cell, or?
Yeah, if for example we use this pair of nucleotides, and then you say that this 100% there is a secondary structure element here.
Okay, so I would say for RNAs, when they float around in the cell, there's like a very, very high probability. I would say there's always a secondary structure, just because it is more stable. So this, like, if there isn't a secondary structure, then the molecule is simply too unstable, and it kind of always goes the stable way. But the task here is not that whether there is a secondary structure or not. The major task is what is the actual secondary structure, because all these regulatory roles these molecules play does always often depend on the exact formation of the structure. And you can imagine that for even such a small molecule like this example here, there are several possibilities how that could form. It could look like this, but of course, like, I don't know, here's a G and here's a C, so these two could also pair, and then the whole secondary structure would look very, very different, and that would change the whole regulatory circuits around it. So that's the major task, is what exactly is the secondary structure. Did that answer the question?
Yeah, okay, but do you know also other, like other features which not this pair, for example, but other also terminators for these secondary structures, except this one which you investigated carefully now in your presentation, looking at the neighbors and also at some mutations which may exist there. But do you know also other stable combinations?
Other stable combinations of an RNA molecule or other ways to terminate this process?
RNA molecule, which also showed for secondary structure with high probability.
I'm not sure if I did understand the question. I'm sorry.
Mm-hmm. So I mean my question once more. I just repeat. You provided us the combination of RNA nucleotides which with high probability tell us that we have here a secondary structure of RNA.
Yes.
Yes, and you investigated quite carefully for example, for when some mutation exists, also how this secondary structure depends on these mutations. Is it? Yes, and other like features which except this one exist, or do you know also because you studied only like one initial starting point for your research.
Okay, yeah, there are other factors on which the stability of an RNA molecule depends on. It can, for example, be bound to a protein, so a larger molecule which stabilizes it. There can be also, like I'm now looking at the secondary structure, which is kind of the 2D structure, but they can also, I mean, this is a 3D molecule in a 3D world, so obviously it's going to build 3D, three-dimensional structures as well. So there are many other factors, but in the case of the terminators, these are quite simple structures. So these are actually normally, or as far as we know, they are not stabilized by a protein or anything like that.
Okay, thank you very much.
Yeah.
Thank you. Some more questions? Okay, and Vivian, thank you very much again. And we go ahead to the next presentation. And next presentation will be given by Niels Förster from the same university in Bochum. And he is also a PhD student. And the topic is reliable identification and quantification of toxicological dose response in microscopic images of neurosteres.
Yes, thank you very much. Let me just share my screen real quick. Okay. Okay, can you hear me and see my screen?
Yeah, everything is okay.
Okay, great. Yeah, thank you very much for the introduction and for the opportunity to present our work here. My name is Niels, and I will tell you about the reliable identification and quantification of toxicological dose responses in microscopic images of neurospheres using deep learning. First off, a little bit of background. On the right, you can see a figure from 2006 displaying the, at the time, known chemicals, the quantity of those. And as you can see on the top, 5 of those were known to be toxic to human neurodevelopment. This developmental toxicity, short DNT, can be defined or can be attributed to a chemical if it displays adverse effects on neuronal cell development. And it is important to know this DNT profile of a compound, for example, if you want to release a new drug on the market. For this project, we have partnered with the Leibniz Research Institute for Environmental Medicine, short IUF, in Düsseldorf, Germany. And there they have an assay that can reproduce this neuronal development in vitro. And this can then model and test the DNT profile and DNT effects of different compounds using the neurospheric model. So then we can model the DNT profile of a given compound. Talking about the neurospheric assay, a real quick introduction to that as well. First off, 3D neurospheres are plated, are grown for up to 7 weeks. These originate from human neuronal progenitor cells, and then it takes 3 to 5 days after that, where they are plated on a 96 well plate with 1 neurosphere in each well. And then they're also treated to a differentiation medium and differing concentrations of a potential DNT compound. As you can see here, this differentiation changes the stem cells into radial glia cells, neurons, oligodendrocytes, and astrocytes, with a neurosphere having a size of about 5 millimeters each. Besides the different media, the cells are also stained using antibody staining to highlight the nuclei, the neurites, and the oligodendrocytes, which is what this work will focus on. As you can see here on the right, I have shown you an example of the neurite staining. This produces a grayscale image that has been acquired with fluorescence microscopy. You can see in this grayscale image that the higher the signal intensity, the more this responds to the antibody staining. And as you can clearly see, there are quite some neurite structures. Now, since we have 3 stainings, we can acquire 3 signals, and then we can combine those to this pseudo-color image. And as you can see here, you can see the nuclei in the blue color channel, the oligodendrocytes in the red color channels, and the neurons in the green color channel. As stated earlier, this seems to be from a neurosphere that's been treated with a control, because this is grown very rapidly and very healthy. But if it were treated with a potential DNT compound, it would look quite different. Then these images can be analyzed to observe different DNT effects, and those can be categorized into 3 categories. The first of being the quantification, meaning that we'd like to know what cell do we have and where is it located. The migration being how far has the neurosphere itself grown and expanded, and the morphology that describes the the morphology of the cells. For example, endpoints like neuron length or something like that. In this work, I would like to focus on the quantification endpoints. And now let's take a look at how those can be displayed and measured. This is usually done in practice using dose response curves. Here we have, I've shown you the results actually of our models to show that they can reproduce the 2 known DNT compounds, one of those being quicksilver and the other being tetrabromophenols A, with those having an adverse effect on the neuronal differentiation and the oligodendrocyte differentiation, respectively. Also, we have plotted ibuprofen as a control. So let me real quick explain what you see here. This is the result of a curve fit with here, as you can see, the different compound concentrations, with every dot representing 5 or more neurospheres. And as I said earlier, this results from a sigmoid curve fit. On the x-axis, you can see the normalized concentration for a respective compound, and on the y-axis, you can see the impact of this endpoint that this given that this compound has made at a given concentration. For example, here in the controls, you can see that with increasing concentrations, it doesn't really affect the endpoints, as it's constantly staying near 100% relative to the control. But with the known DNT compounds, you can see that that it has an adverse effect on the endpoint with increasing concentrations, which is actually expected. Then this can be measured. Then the IC50 can be extracted from this metric. What is it? The IC50 stands for the inhibitory concentration, at which 50% of an adverse effect has been reached compared to the control. For example, here it would be something between 2% of the concentration for this compound. This is an important metric to determine the DNT effects of a given compound for each endpoint. I've been talking about deep learning, so let's get into that. First off, here is a quick overview of our training data. As stated earlier, we grew neurospheres and we organized them into 1996 well plates with one compound dedicated per plate, and on every plate there was one neurosphere each in per well, with 8 different compounds tested. With 8 different compound concentrations and 5 technical replicates. Meaning that we have grown about 40 neurospheres per plate. Here on the right, you can see then the data distribution with, in general, 36 of those neurospheres being distributed into the training data set, 4 into the validation data set, and then on these last 4 plates, we used 4 neurospheres for an independent test data set. This table also shows some confounders. For example, you can see that we have stem cells originating from 4 different individuals, and we tested 13 compounds overall with differing DNT effects. Or maybe none, maybe this was a control. They were all blinded at the time, the compounds. Then we used staining for 11 neuron antibodies, and for 16 oligodendrocyte plates were stained with some overlap. And as you can see, because of this this discrepancy in some of the stainings, we decided to actually train 2 different neural networks using the same processes in both, just to maximize the data available. For pre-processing, first off, we manually adjusted the brightness of every color channel, and then we placed 2 regions of interest per neurosphere somewhere here in the migration area, and these regions of interest were about 700 times 500 microns. Then, as a next step, we annotated every single nucleus within a region of interest and determining if it was a neuron or an oligodendrocyte. And then to process the data, as you can see here, with every nucleus in the center, we placed the 64 times 64 8-bit RGB image around every nucleus to feed it to the neural network. The general idea being that with the training and with the model obtained from training on the regions of interest, we could predict the quantifications on the whole migration area of a neurosphere. talking about the model, for that we modified VGG model architecture, and as stated earlier, using one model for oligodendrocytes and one for neurons. Some more training data. Overall regions of interest that we placed. These contained about 200,000 individual nuclei that were placed in the neuron dataset, and 300,000 for the oligodendrocyte dataset. And from those annotations, we could see that roughly 1 out of 5 nuclei was annotated as a neuron, and 1 out of 12 was an oligodendrocyte. This was quite the data imbalance, but we will get to that later. First, let's talk a little bit about the training. We trained for about 5,000 epochs with early stopping enabled to prevent overfitting, and with 100 batches, and we chose the binary cross entropy as our loss function. We implemented it in TensorFlow, running on a GPU server with 4 NVIDIA GeForce GTX 1080 Ti graphic cards. Coming to the results, first off, we tried to look at some normalization approaches, because when you stain a neurosphere and use fluorescence microscopy, your data is very much dependent on the staining quality and lighting conditions at that time. And such, we tried different normalization approaches, as you can see here. We compared them for the neuron and for the oligodendrocyte dataset each, and every graph you can see here in this precision recall curve is an individually trained model on the training data shown you earlier. You can see here that the area under curve, if we do no normalization or just normalize for the 8-bit values, so normalize between 0 and 255, yields acceptable results, but those can be improved if we not only normalize each single tile, but we normalize it in context of its originating well. One highlight I would like to show you from this is this model that we trained here. In this case, we used the minimum and maximum values of just for each cell individually, or for each tile individually, over all 3 color channels. And as you can see here, the performance dropped quite a bit, showing that it's very important to keep your staining and brightness values in check if you want to use fluorescence image data. Another thing that we did was we did an internal validation. In this case, we trained a single model using only training data or only information from individual 1. And then we tried to predict the other individuals from the data learned or from the data derived from individual 1. As you can expect, the best areas under curve were achieved when predicting the same individual with itself, but still yielding acceptable results for other individuals, and of course an average result for all individuals combined. Showing that it is important to keep this confounder in mind and maybe mix up your training data with different individuals in this case. Some other results that we had. I hope that I have convinced you that we have trained a robust neuron and oligodendrocyte classifier that has a lot of confounders accounted for and is validated on the IC50 or can reproduce expected IC50 values on the DNT spectrum with known DNT compounds actually being determined as toxic and controls as non-toxic. Also, as you can see, we made our annotations specifically for toxicology because the morphology differs quite a bit depending on the DNT compound and concentration being used. Actually, some regulators have shown interest in our endpoints and in the assay. two of those being the Environmental Protection Agency in the USA and the European Food Safety Authority. And for our future work, we think that we can extend our classifications, capturing also radioglial cells and astrocytes. First of those is for the firma. There's already being preparations made in the lab at the IUF. And then with all this training data that we already have, we could try to expand it using weakly supervised learning to maybe infer morphological endpoints. Yeah, that brings me to the end. I would like to thank everyone involved in this project. And yeah, does anyone have any questions? Very important, we have recently published this work, and you can see the source code and some example data on our GitHub page, linked below. Thank you very much for your attention.
Thank you very much for a nice and deep presentation. Please, questions.
Thank you very much for your presentation, Niels, because I'm not skillful in this part, which like your application part, but I would like to ask a bit more about this part when you already have fluorescent images and you are trying then to classify, right? This these microscopic images in several classes.
That is true. Yes.
And at this moment, your classification, how good it is, and how many classes you now at this moment you are using for your classification?
Yeah, currently we do have technically we have two classes, one being for the neurons and one being for the oligodendrocytes, but stemming from two binary models. So the idea being that if we know every nucleus inside of this in the migration area, we can extract this like the context of this nucleus and feed that to the neural network, and then the network decides what kind of cell it is, and then we can feed that back into the neurosphere and match it with the migration area to count the actual or the overall number of different cells within our neurosphere.
And how then this like classification results they relate to toxicity of?
Yeah, as stated earlier, you can count the number of nuclei that is inside the migration area. So, for example, you can see that here. If we normalize the number of nuclei, for example, or the number of oligodendrocytes here on the right, or the number of neurons on the left, and then we can see that with increasing compound concentration, for example, for the control, the number of nuclei, the number of oligodendrocytes, and the number of neurons doesn't really differ.
Okay, and exist also other classes, or you just these two are the most important for your study?
At the moment, yes, but we are in preparations of capturing more of those cells, because those are the main cells that differentiate from the stem cells, and it's also a staining problem because you cannot really stain or really overlap all those different antibody stainings.
So these two other classes are not visible in your images, or I'm not right?
Not yet, because they are not yet stained. Yeah. I think Axel wanted to say something.
Maybe Niels, you can come. I mean, so this is one endpoint that you described, like how many cells differentiate into neurons or oligodendrocytes. But of course, in the overall approach for this essay, there are a lot of more endpoints being measured. So maybe you can just give a broader picture. What other features, what other endpoints that are neurotoxically relevant one can extract from those images?
Yeah, sure. As stated earlier, there are three categories. For example, the quantification, that is again staining based, because that's the information that we have currently with our staining, to identify the number of differentiated cells and where they are located within the sphere. For example, and maybe then you can extract like the cell density at different migration distances, which is one endpoint being measured. And for example, for the morphology, we do have an image analysis approach that uses skeletonization to identify the neurite length and the branching points. As such, one can like measure the interconnectivity of the neurons within the neurosphere. As Axel stated, this is there are a whole lot of endpoints that we can already address within the neurosphere, but due to time constraints and I just wanted to focus on the quantification, because this is basically the pillar that every other endpoint is resting on, because if we don't know what cell is where, we cannot really infer any other endpoints from that.
Okay, thank you
Does
very
that
much.
answer your question? Okay, thank you.
Thank you.
Thank you. Maybe more questions, please. Technically, I'm very much impressed about 5,000 epochs of training. So
yes, sometimes
because you start from scratch, or you start from using pre-training.
No, it's all from scratch. Of course, sometimes they terminate earlier. Sometimes sometimes they take the 5,000 epochs, but it's just a general metric, because as you can see here, we did we trained many model candidates to show different confounders. If we do have the time, I have actually prepared some more trainings and some more models checking.
Maybe you can comment on the challenges of utilizing pre-training.
Yes, sure. As stated earlier, there are some publications out there that that try to model, for example, the ideal morphological what is it called? Conditions of cells that we do not really have on high compound concentrations of DNTs, which quite which quite like impact the morphology of these neurons or these oligodendrocytes, which would a pre-trained model not really detect. Also, there are like we stated here, there are quite some different confounders in the brightness values that we encountered, as well as the as you can see here, there's quite the network of cells, and quite let's call it chaotic chaotic data set that we can have here, and inferring individual cells from that might prove quite difficult.
Yeah. Okay. Thank you very much. Okay.
Yeah,
so it's very interesting presentation. Very interesting domain. You are lucky to got it to research in. Okay. Good. So let us go ahead, and the last but not least, as usual, presentation should be done by Anjani, and she is from, I may be not correct, Haute École de Gestion, and okay, and the topic is DISTANT-CTO co-training for clinical named entity recognition. That's the title. Anjani, please, the floor is yours. Okay. Go ahead, share the screen.
Yeah, just give me a moment.
Yes, of course, as usual.
Can you see my screen?
Yes, we do.
Okay, yeah. Thank you for introduction, Dr.
Sorry,
Kovalev.
it doesn't fit the screen, so we don't see everything. We see like 90% of it.
Okay.
If there is no important information on borders, you can show it like that. Yeah, perfect.
Is it better?
Yeah, much. Thank you.
Thank you for pointing this out. I think it's afternoon there, so good afternoon, everyone. I will be presenting DISTANT-CTO. I have changed the title a bit. It's Distance Supervision for Clinical Named Entity Recognition. PICO recognition is an information extraction or named entity recognition task whereby when given a clinical document or a clinical trial document, our task is to extract the spans of text that describe PICO. P in PICO stands for participants, which are the patients that are involved in a clinical trial. I stands for intervention, which is either a drug or a procedure or a therapy that's under the investigation in the clinical trial. C stands for comparator, which is an alternative intervention that's being compared to the main intervention in the trial to see if the main intervention actually works or not. And outcomes are the measured intervention effects on the patients. For example, in this one, you can see that the patient or the participant span that's extracted contains information about the sample size of the patients used, their gender, and if they had some disease. Now, PICO extraction is easy unless it needs to be done for tens of thousands of documents. And this is specifically the case in writing systematic reviews, which are basically a way to systematically answer one single well-defined clinical or research question by examining every piece of literature available out there. So to just answer one question using as much evidence available out there, it takes a lot of time, but it's really necessary because it's official and it's used for evidence-based clinical practice and health-related policy making. For example, if a government puts out that wearing 2 masks instead of 1 can reduce the chances of contracting COVID, there better be a systematic review behind it. So where does PICO recognition fit in systematic reviews? One of the first steps in writing a systematic review in answering a clinical question is actually document filtering, which involves 2 reviewers manually checking each and every document to identify if relevant PICO mentions are present in the text. And only if all the relevant PICO mentions are present in the text is the document included in writing a systematic review. If 1 or more PICO mentions are absent, it has to be excluded. For example, if you are writing a systematic review that concerns COVID-19, you will only want to look at the evidence that mentions patients who had COVID-19. And if they do not mention it, it has to be removed from writing a systematic review. This process is really, really time and resource consuming because it involves physicians and clinicians and medical professionals analyzing these documents. And it's not their task. They are paid to do this, but then they are not doing the actual task, which is treating the patients. So what one can do here is bring in neural networks, and probably they could help us identify PICO mentions. But the problem is that neural networks require really large data set, and the only available large entity annotated PICO dataset that we have right now is EBM PICO, which was released in late 2018 by Nye et al. And this is called as a large data set, but it contains only 5,000 PICO annotated clinical trial abstracts, not even full papers, it's just abstracts. Now, the people that released this data set belong to a really large institution, and they've literally hired crowdsourced workers and physicians. They trained them to annotate for the PICO, and it really costed them a lot. Now, Those people who are working alone or who are not placed in very structured projects, they cannot bring about innovations in this field. Another thing is that such corpora are really static. So once the annotations are done, they are done, and then they are there for like 5 to 10 years. Nobody changes them or nobody adds to them. They become static, and over time, probably they become insufficient and irrelevant for real world applications. Another thing is, especially about the EBM PICO corpus, is that, or any other manually annotated corpus, is that it's really domain specific and it cannot be easily extended to the other categories. For example, the EBM PICO corpus is only limited to Alzheimer's disease, diabetes, and cardiovascular disease. Another thing is that this corpus is also limited mostly to the pharma domain. So it doesn't cover other therapies like physiotherapy, rehabilitation. It doesn't cover complementary medicine, surgery, or biologics. One of the ways to challenge this bottleneck is to use distance supervision to obtain large-scale, imprecise labels for unlabeled corpora without using any kind of human intervention. A lot of examples of distance supervision have been demonstrated for relation extraction, especially in the health domain, but there are very, very few examples for named entity recognition or information extraction. And there exists no example for PICO recognition that was supported by distance supervision. In this work, what I do is I try to examine whether distance supervision could be used with semi-supervised learning to improve intervention and comparator extraction. I limited it only to the 2 entities because first I wanted to check the proof of concept whether this thing could actually work for at least 1 or 2 entities. And so if there is a lower level of failure here. Semi-supervised learning is applied when you have a few strongly labeled data points, abundance of unlabeled data points, and a set of weak labeling operators that could sample from this unlabeled data and label it. One of the weak labeling forms is distance supervision, which in natural language processing is essentially database lookup combined with pattern matching. So once you have this few strongly labeled data points and programmatically labeled data, using distance supervision, you can combine both of this and conduct semi-supervised learning for your application. One of the most common forms of distance supervision in natural language processing is to heuristically align structured information from a database onto the unstructured text. Here, your structured information will be your entity of interest, which you want to align over an unstructured text and essentially obtain your annotation programmatically. So the labeling operator here tries to fuzzily match the longest common substring between the structured information and unstructured text to identify whether they actually fit with each other. The method to align these 2 forms of text is dynamic programming. It's one of the methods to align the text, and after the dynamic programming, which identifies where are these matches located, you can use Gestalt pattern matching to identify the similarity between 2 strings, which is the structured information string and the unstructured text string. The similarity is calculated using the formula here, which measures twice the number of matching characters divided by the total length of both the strings. And this similarity lies between 0 and 1. Now, to actually generate such a programmatically labeled data source, we need something that has the structured text information and unstructured text information. And one such database that has been completely unexplored for this thing is clinicaltrials.go, which is maintained by USA. It's a database that documents more than 300,000 clinical trials from all around the world. And the information entered in this database is manually entered by the principal investigator of trials. So just imagine a lot of manual data, like manual entries, that this is the manual labor that's stored in this database. With this example, this is examples of one of the clinical trials stored in the clinical trials org or CTO. And you can see that it stores the title of the database, it stores the title of the clinical trial, it stores the description of what's happening in the clinical trials. And this is essentially the unstructured text form because these are like complete sentences. It also contains some structured text information. Here you can see the name of the intervention is literally mentioned in the table. So you see that there is this name of intervention with its labeled intervention name or the treatment name. And then there's also patient condition that's mentioned. There's also phase information there. So essentially now we have structured information source and also unstructured text source. And what I kind of assumed after examining like 10 to 20 dry tests on clinical trial records, I assumed that each clinical trial record in CTO could at least have one structured source of intervention name, which could somehow be mapped onto the unstructured text targets. So each intervention name that's there in the table is possibly mentioned in one of the descriptions or title. And this means that when you see the intervention name here, if it could be aligned and scored, it could be identified in these different targets. And when we extract it after the alignment, we can see that intervention names are now automatically or programmatically labeled without using any manual label. So let's go through the methodology of candidate generation, where we assume that there exists such a mapping, and we define a process of generating these distantly labeled sentences with intervention annotation. I first crawl the entire data set, retrieve the studies in JSON format, and stored it in a local Elasticsearch document index. After that, each study was pre-processed by adding some post tags. Punctuations were removed, lower casing was done, and we also performed sentence tokenization for any text that was longer than one sentence. Next is the task to actually extract the sources of our structured text and unstructured targets. For our example, we chose intervention name and intervention other name as the source set from each clinical trial record, and we chose titles and summaries as our targets where we would match sources onto. To actually match the source with the target, we use dynamic programming to identify location of the match. And once it is identified, we try to score the match using Gestalt pattern matching. Here we see that the source, which we saw in the previous example, consolidative therapy, really actually matches the target. But if we try to measure the similarity using the formula that we saw previously, it would be seen that the match is really only 0.52. We as humans, we understand that, okay, this source completely matches the target and it should be extracted, but the similarity formula that we used actually matches the complete source with the complete target and reduces the amount of, or reduces the similarity score. So what we do is we modify the similarity score a bit. We take the block from the source and the target that completely matches, and we modify the formula of similarity to identify where exactly the to identify if the source completely matches the target by dividing the length of the match block, which is basically source and target matching divided by the length of the source. This again falls between 0 and 1. 1 means there is complete match, 0 means there is no match. Now we have the formula to identify and extract this kind of matches. And if this modified similarity is more than equal to 0.9, we map the source term to the target sentence and generate a positive annotation sentence. If this modified similarity is less than 0.2, we take this target as a negative annotation sentence, meaning no annotation of intervention was found in this target. We carry out this exercise to actually add in the negative annotation sentence, because in the real world examples, it will not only always be the case where intervention is mentioned in the sentence. Maybe the intervention is not mentioned in the sentence. So that's why we add like positive and the negative annotation sentences and generate a distantly annotated data set and call it DISTANT-CTO. We have the distantly annotated data set, but for the semi-supervised learning, we might also need, not might, but we also need manually annotated data set. And for this one, we use the previously mentioned EBM-PICO annotated set, which comes pre-divided into training and evaluation sets. The training set was used in combined semi-supervised learning training, and the evaluation set was used for final evaluation. But because this set was mainly laden with examples from pharma domain, I annotated an extra physiotherapy set, which contains 153 randomized controlled trials annotated by me. This was to check whether the procedure actually improves or generalizes well on other clinical domains or not. After we have both the programmatically labeled dataset and the manually labeled dataset, we can now train the model, and we train just a simple modified version of the usual state-of-the-art named entity recognition model. Here we use two kind of features. One is BERT-based contextualized features, and they are combined with the one-hot encoded post-tag features. This is followed by a bi-LSTM layer, both of, adding two LSTM layers, which are just concatenated. On the post tags, we apply self-attention because I kind of noticed that post tags carry like a bit of a generalization signal. For me, it was not possible to add attention or also on the CyBERT features because of the time constraints and also because of the number of GPUs that are shared among the group members. After that, the attention-weighted post tags and the attention unweighted by LSTM contextualized vectors were concatenated, shallow concatenated, and this was followed by a CRF layer that kind of learned whether a token was intervention token or if it was not an intervention token. We did 6 experiments to check whether our approach works or not. And these 6 experiments are divided into 2 categories. First category is experiment series 1.x. In experiment 1.0, we just use the programmatically obtained data set, but we used all the annotations that had similarity score of more than equal to 0.9. So this included some scores which were not as perfect as similarity of 1. In experiment 1.1, we limited the DISTANT-CTO annotations only to those annotations that had like a score of 1, and we removed all the 0.9 candidates. In experiment 1.2, we again used the modified score of where the similarity is 1, but now we remove the negatively trailing sentences. Experiment series 2.0 is the same as experiment series 1.x. But here, in combination of using DISTANT-CTO, we also use EBM-PICO training set to see if adding like manually annotated data set would improve something or not. All these experiments were compared with 4 baselines, the references to which are given in the references section. And this baselines only used EBM-PICO training set because, of course, they did not have access to the DISTANT-CTO. And baselines were only evaluated on EBM-PICO evaluation corpus, while we evaluated it on 2 domain-specific corpora. Our candidate generation process actually resulted into more than 1 million sentences that were annotated with intervention entity, and at least 200,000 entities were extracted and mapped onto the targets. And you can see the number of annotations that we obtained with DISTANT-CTO far exceed the number of annotations that you can get with EBM-PICO, even after paying a lot of annotation fees. These are the results. As it can be seen from the table, training of our SSL system using only the DISTANT-CTO still crosses the state of art, which is baseline 4 by 2%. Combining DISTANT-CTO with EBM-PICO increases the state of the art by 5% because it clearly increases the recall of the process. But we also noticed that using low confidence annotations and programming labels reduces the F1 score for the physio data set, meaning there are some more noises that we are adding to this annotation by adding the low confidence matches. But adding low confidence matches actually improved the macro average F1 scores for the EBM-PICO evaluation set. Another thing that we observed was that adding the negative annotation sentences to the positive annotation sentences brings about positive change in the macro average F1 score for all the examples, but this is a bit sad because then the experiments or the system really depends on the structure of the input text, but it still brings out positive change. At the moment, we did, for this study, we did not address participant and outcome entities, but currently we are extending it to these other entities. One other problem that we have is noisy labels and false negatives, because if you see from this example, we have the name of the intervention that has no direct way or no easy way to align from the source to the target using the dynamic programming and the Gestalt pattern matching similarity that we are trying to use. So this essentially will be missed out. Another thing is that this kind of annotation programmatically will cover some intervention, but other interventions will remain uncovered. If you see this example of consolidative therapy, you see that the source or the intervention name or the intervention that's being used in the clinical trial is mentioned in the study, in the targets, but there are other names of interventions that of course are not used in this study, but they could have been used as interventions in other studies, and within the DISTANT-CTO corpora, they will be marked as intervention somewhere else. If humans were annotating it, they would have annotated this as well. But because machine did not annotate it, it will bring about much confusion for the machine learning system. So these are some of the cons of our process. Here, we gave a zero-cost methodology to obtain annotations programmatically for intervention and comparator annotations across 11 intervention types. And we crossed the state-of-the-art system without having to invest a lot of money into getting the manually annotated corpora, which is not even feasible for like really large corporations. They think twice before starting a manual annotation project. And especially if people are working alone, it's a bit challenging to bring about innovation, even if you want to bring about innovation in some field, especially for something like automating systematic reviews. The problem is that a lot of people have started working on it, but there are more companies working on it compared to more researchers. So researchers are at a disadvantage of not having enough manually labeled corpora, which is just locked in the companies. And I'm currently extending the work to all of the PICOs by designing new weak labeling operators and methods to merge them, which will be generative methods. And we are also trying to reduce the number of noisy labels by exploring the fuzzy pattern matching, but this is the ongoing work. And thank you very much. Any questions?
Okay, Anjani, thank you very much for your presentation.
Thank you.
Now, please, questions.
A very simple question. Thank you very much for your presentation. Why when you are discussing your results, the same words, like couple of words, are underlined with lines of different colors? One is with blue and another one with green. What does it mean?
Do you mean in this one?
Oh, yes. Not this one, but maybe close to the end. Your discussions nearly at the end. Oh, here, right. For example, here, consolidative radiotherapy, and here is in blue, and here is in green.
Yeah, this is because I wanted to differentiate between the source and the targets. The source is colored only a bit differently, but I think they appear quite similar colors. The source is colored in like green and the targets are colored in teal, but I should have used other color for the targets. I just wanted to differentiate between the source and the targets.
Right, but okay. So source in blue and target in green, because here.
Sorry. Yeah. Sorry.
Okay. Thank you very much.
Okay. Just note, at certain time I was studying color differences between male and female subjects, and specific studies suggest that dealing with color in female is much more rich than in male, and vocabulary about colors is also much larger in female comparing to male, and many other things. I'm not even talking that color blindness or blindness or color deficiency mostly happened in male, but not in female. So in color space, we are not that strong as women are. Okay, anyway, please, more questions?
Yeah, maybe one part I maybe just missed, or one detail regarding the Gestalt pattern matching distance that you used. So you basically you use the dynamic programming for identifying subsequences of words, I guess.
Yes.
So words are the basic tokens. Okay, and then this would discover constellations of words that occur in the same order, right?
Yes, yeah.
Is that, I mean, are the reports sufficiently structured that the relevant words tend to occur in the same order? Or do you maybe miss some constellations of keywords because they flip the order in different trials?
Yeah, this is the case. We have a lot of false negatives because consolidative radiotherapy will be mentioned like consolidative radiation therapy. Even this kind of thing, when at least like the word form or the word order changes, we will not be able to match it. So if it's if in source it's mentioned as consolidative radiotherapy and in targets it's mentioned as consolidative radiation therapy, it will not be matched with the system that we now have, because it's trying to match the exact match or a bit fuzzy match, which are like 0.9 similarity score. And the one that you mentioned is really interesting because I saw one of the examples where it said in source home-based device rehabilitation, and in the targets it was something like rehabilitation with home-based devices. And even though it's, you know, as a human that it matches, but because the sequence of words is changed in the source and targets, it will not be able to match it. I discovered one library which is called as FuzzBuzz, and this kind of matches the set of matches. So even if the word order changes, it will still be able to match using like a modified version of dynamic programming and Gestalt pattern matching. And one of my current works to extend it would be using we'll be using this library to address the problem of missing or noisy labels.
Okay, of course, the extreme change would be to just consider a document as a set of words, but I guess then it's too extreme to just look for occurrences of keywords, totally disregarding the word order.
Yes, I will try to do this as well, because what I wanted to see was that if at least one of the words or one of the terms from my source matches somewhere in the target, I will not label this instance in the target as 0. Instead, I will try to abstain from annotating anything because I do not want to add to the noises. So this kind of considering probably just the source and target as a bag of words might bring about some improvement, but I will need to test this process of abstaining from labeling rather than just considering it as a positive label.
Okay, thank you. More question? No, just technical. So I suppose, Anjani, I suppose your supervisor is Professor Henning Müller.
Yes, yes.
Are you located now in Sierra or somewhere else?
Yes, yes, I'm located in Sierra, Switzerland,
Okay.
yes.
Okay. Alles klar.
Alles
Okay.
klar.
Yeah, well, in Switzerland, they speak all the languages.
Yeah, it was very tough for me because I lived in Germany for quite some time and I learned German. And when I moved to Switzerland, I moved to a city that is just one city far from the German part. So now they speak French. And if I go 300 meters from, like, sorry, not 300, like 3 kilometers from here, it's a German speaking part. And I don't know, because of coincidence or what, I was placed in the French part and not in the German part. So I also had to learn a bit of French.
Yeah. Yeah, okay, that's fine. That's stimulate somehow promotion in languages. Okay, now let me conclude. Now I think this is the end of section number 1, and I think it was very successful in my view, because so nice presentation we collected, and some people expect that they will be, because it's still given by students, they are not that high quality, etc. What is not true, definitely in our case. That first point, so I'm very positive about that. The second point, so we suppose we will continue somehow consider some mistakes in organizing such a workshops or conference, whatsoever, and then we will continue maybe the second one. And there are so many potential students who has something very interesting to present. For instance, Diana Müller, I know from Axel's group, and Joshua Gutke also doing very interesting things, and many others. And also in other countries, there are also interesting things going on, so we will try somehow involve them. And that's the second. And third, what is also very important. So I want to thank our sponsors, who is BASNET and EAP Connect project of both European Union, where participation in. And they sponsored not only that kind of event like this one today, but they also support us with very good communication facilities. They also support with the computer power. And we had, in particular, my group had 1 year supercomputer, access to supercomputers in Europe, and that's very valuable. So we are very thankful for people who are assessing money and different kind of support, especially for young students. And on the back of me, you always see the logo of that nice projects. And finally, so I want to give the word to Alexei Belotserkovsky, finally, to make a group photo of this section. Alexei, okay. Please.
Yeah. The moderator, thanks for passing me the floor, actually. So, yeah, my name is Alexei, and this time I'm standing in sort of a dark corner of the conference, but I'm extremely happy to monitor it technically. And having an opportunity, I would also love to thank again Axel for his great keynote in my conference we had in September. And for this activity, when you grabbed your people to involve in this event. Let me ask you to do 2 things before we go for lunch or whatever. First of all, actually, so we're losing people. We started from 43, and now we have 34, but still, so it is very, very good. And I kindly ask you to participate in a group photo. We will do this actually so in the second session, but still, so I'm expecting less people. But now, please turn your cameras on. Of course, if you do not want to show your faces, I will accept these as your GDPR rules. Yep. Once at least more than 50% will turn your cameras and do like this or something like this. We will make for my signal. Yes, yeah, and please, Anna Karpenko, please help me just to snap screenshots also. We will have more materials to present it
yes.
for our EP Connect project.
Can you please repeat what you told? It was a disconnection.
Okay, so please, I think more or less we have people here, faces. Now please snap a screenshot to your computer, and I will do also the same. Yep. Okay. Please, you may do like this. Yeah, all of you. Yeah. Exactly. So we have also the second screen, so it will be a little bit complicated. Okay. I should say yes. As for me, I'm finished. Anna, have you done something?
Yes.
Okay. Well, the second thing actually. So honestly, I was having a warming up for today's virtual meeting, but now it turns to round up, a little question game before the lunch. Please grab your smartphone, and I will share my screen now. And please, please just type menti.com. Yep, menti.com here, and answer the question now. How are you today, honestly? Yeah, so probably boring or sad or you feel funny or fun or something like this. So it will be nice to just as an interactive part of our virtual event, let's say. You may right now answer this question. I will see.
We need some time to connect.
Yes, of course. Yeah, a bit tight. Yeah.
If you can copy the code in chat, will be better. Because like to copy it.
I think already. So it should be the code is on your screen now.
Yeah, but it's not
quite
comfortable
anyways,
to copy paste it.
A bit tight and sparring. Yeah, it is nice. It will be a cloud answer.
So I think it's asking for password. Is it correct?
No, it is asking for a code, and you see the code. Okay.
Just press submit.
Exactly.
Okay.
Yeah.
Well,
so we
you
have
must
answered.
enter a code to continue.
Exactly.
Which code?
The code is on your screen at the shared screen. 4252 0
okay, I see.
221. Yeah. Okay. At least 5 people already answered. And I will answer also.
0221.
Enough. Yeah. 252 021. Okay. Yeah. So things are going now. So this is a type actually. So how we do this interactive. I'm sure that partly you already experienced in these things, but there's a conference. This is a conference. The idea of this conference is involve students, since involve them to new activities. So probably for some of them it's already known activity, but for some of you it is new. So please try to be with us. Try to learn these interactive themes, and I think it is funny enough. Let's say. Yeah. Well, sad. Yeah, someone answered sad. Unfortunately, but actually, so what should I say? What I'd like to add that this time. So I was moderating the conference called Partner Recognition Information Processing in September, and comparing to that conference, let's say for big guys, for scientists, this event is also good, and it it has a good narrative, it goes smoothly, and your English is very perfect. Well, of course, those who are in Germany or Switzerland, well, they already have good language, but still, so as our foreign colleagues know, that Russian is extremely different compared to English. It is quite difficult to think in the same language. But now I think that it's very important for students to understand what is going on in the world, in science, in scientific world. It means that we have to speak in the same language. So and I'm happy actually. So what is going now, and also what I'd like to add that this event we call STUDATA. It means, well, students and data. So this time it is for biomedical and bioinformatics. But I hope that we will keep this tradition and we will proceed with this event. And next time probably we will have something more common and more, let's say, close to me as a scientist in the field of satellite data processing. Probably it also will be very quite interesting for you, but still, well enough. Okay, smiling. Well, yeah, I hope that the word "sat" will be smaller and smaller as a cloud, because MC this event is quite good. Okay, let's go to the next question, on the very obvious question, but please answer. Yeah, just refresh and answer this question. Where are you from? I'm expecting 2 countries actually.
No, could be 3.
3, okay. Well, why not?
Well, even 4. There was someone visiting from Russian Federation also, but not now. He's not here.
Yeah, but Germany is a big, you know. I'm India, yeah, of course. Yeah, Belarus is now, but still Germany is the biggest.
Well, Lithuania also should be here. Well, depends.
It depends.
Not now, but previously we were traveling intensively. So
this is a data processing actually. So you see, the result depends on the set we have, because according to what we have a picture now, Germany is the most important country in this event. Yeah, but I'm actually, so I expected Belarus more than Germany, but still so.
So we also got Norway.
Yeah, Norway. Nice. That's great.
Well, actually, by the way, in Norway, we have with Axel, we also have links to Norway, to the group in Norway. So perhaps we need to involve also people next time from Norway, from Norwegian University of Life Sciences.
Yeah, that's how we're traveling during COVID-19.
Yes.
Yes.
Just watching pictures of nice countries.
Exactly. Okay, so silence.
In Norway, we want to travel in summer anyway, not in winter.
Ah, okay, yeah. Exactly.
Otherwise, you will see just snow.
Well, thank you all. Well, 12 answers. It is more than nothing, at least. For others, I hope you will join our warming up. Let's say warming up before session 2. I have the second warming up, and then Hannah, you may just announce the second session, and you will be the only one who in between lunch and us.
Yeah, thank you. The second section will start in 40 minutes. You can also use that link. We will start at 2 p.m. on the Belarusian time. So you're welcome. We will speak about using artificial intelligence in the bioinformatics. Especially, we will focus on the drug design. So you're very warm welcome, and we will try to make it interesting for you and waiting for all participants.
Thank you. So see you after this lunch break, let's say.
Okay, goodbye, everyone. Goodbye.
Yes, good afternoon, everyone. I would like to say a warm welcome on the second part of our conference. We will start from the welcome word from Professor Alexander Tuzikov. So please, Alexander, open our second section.
Okay. Thank you very much. We are nearly ready to start the second session of our conference. We already participated at or at least some of us participated at the first part of this conference, and we divided this conference in two parts. The first part was mostly related to images, processing, recognition, medical imaging, and also text processing. The second part relates more to processing analysis of genomic data. So here in Belarus, we have a department at the Belarus State University, department on biomedical imaging and information processing. The department is called Biomedical Informatics Department, and we teach our students to image processing and also to bioinformatics, and also some problems of computational biology. And therefore it was an interest from our side not only to discuss these subjects and the topics at this circle of our groups, but to extend it and maybe to organize the conference like this. And as we can see from the first part, it's quite interesting also to hear students and graduate students and PhD students working in other places, not in Minsk only, but also abroad. And it was very interesting to hear people from Lithuania and Switzerland and Germany. And probably we will continue further this good experience, but this our session is smaller than the first part of our conference, but still, if we will like organizing such events, we will continue it in future. So now I would like to announce our first speakers. It's our colleagues Nikita Shuldov and Artemy Yushkevich. Nikita is a master student, 6-year student in Belarus State University, and also working part-time in our Institute of Informatics Problems of the National Academy of Sciences. Artemy also recently graduated from Belarus State University from physics department, but now moved to Germany. And I don't know exactly who will present their joint presentation now, because I see that Artemy is participating. I don't know whether Nikita also is the subject of the title of this presentation is Development of Molecular Autoencoders as Generators of Protein Inhibitors, Application for Prediction of Potential Drugs Against Coronavirus SARS-CoV-2. So please.
Before our colleagues start, I would like to say 1 minute about the organization stuff. I ask our presenters to be on time. Please to see that your presentation should be in 50 minutes. If it will be longer, I will stop you. And also I would like to tell that in the end of the section, we will make a group photo. So please be ready, and thank you for your attention. Nikita, please start your presentation.
I will. Hello, everyone.
Hello.
So I'm going to share my screen right away. Can somebody please confirm to me that you can see my screen?
Yeah, all is fine. We see your screen.
All right. Hello, everybody again. So the work that I'll be presenting is called the development of molecular autoencoders as generators of protein inhibitors, application for prediction of potential drugs against SARS-CoV-2. So this is our team. It's not the whole team, but these are the main participants of this particular work. So we are based in the United Institute of Informatics Problems and the Institute of Bioorganic Chemistry. And our main expertise is computer modeling of novel drugs. So without much further ado, let's jump into our pipeline of modeling drugs. So here's a rather general way of doing drug design. Usually, each disease is connected to some protein, which activity needs to be enhanced or silenced by a compound that we call a drug. In order to find best compound candidates for the target protein, one should do the screening of existing compound databases or generate compounds and estimate compound fitness to the protein using a set of molecular model methods, basically. So obviously, almost each team around the world works in their own unique way. They have their own unique pipeline. So this is a rather general overview. So with machine learning conquering almost all spheres in the world, of course, question arises, how can we apply machine learning in our tasks here? And in our work, we have developed the deep generative model and incorporated it into the pipeline in the way that I will show right now. So this way we're capable of enriching the compound sets, our compound sets at early stages of computer modeling, and then when we do further steps, which are more, which perform more accurate computation and modeling, we have more compounds and we have better compounds. So, one moment. Yeah. So the basic idea in our work was to be able to enrich existing pipeline with new potential inhibitors based on the ones that we had already identified using the screening procedure. However, in the case of our model, we're not restricted to database compound only. So we can use our generative model to generate compounds that are not even in the databases. And we also sort of get away a little bit from the bias of the pharmacophore model that that's used in the screening. So we had the following motivations for using the generative model. First of all, if any of you worked with the databases with compound databases or work with screening, you probably know that similarity search is quite often used in drug design as well. It enables finding new compounds, but it enables finding new compounds only around a set of selected compounds usually, right? So you need to use some similarity metric and usually threshold, and then you find new compounds based on the compounds that you have. But our type of models allow for a more thorough examination of the molecular space. And not only that, it enables us to generate from quote-unquote good parts of the molecular space. So we can capitalize on pre-computed value of the free binding energy for the compounds used in the training the model. That are the compounds that we had found using the screening procedure, and then we can try to identify parts of the molecular space where the good binders of our target protein are. And finally, we can use our compounds as the compounds that we already found as existing as source compounds to generate other compounds from. So I'll talk about it a bit later. So let's touch upon the type of data that we fed our model to with. So molecular fingerprints are quite well-known type of way to vectorize molecular data, and it is what's oftentimes used in supervised problems or for the similarity search as well. But they have one big flaw. Usually, when you have a fingerprint, there is no easy way to restore the original structure of compound or several compounds which the fingerprint belongs to. So this becomes especially crucial when dealing with compounds that are generated artificially and compounds that are not necessarily found in databases, right? So in our work, we used SMILES notation of chemical structures or vectorized SMILES notation to be precise. So it has a lot of benefits to it. First of all, it captures both qualitative and quantitative aspects of compounds, in contrast to what fingerprints usually do. Of course, it's easy to vectorize with natural language processing techniques. It's also a type of data which is sequential, so it makes sense to apply LSTM networks to this type of data. Also, CNN networks make sense as well. And yeah, they're very flexible. It's easy to preprocess them. We can have a fixed vocabulary of only those atoms which can be found in drug-like molecules, right? And yeah, I think this is it. So to quickly give you an idea of how the preprocessing was conducted, we reduced the SMILE dataset to that only containing drug-like atoms, as I mentioned, also filtering out based on length, so that our model so that we have less parameters and our model is less prone to overfitting. We also get rid of duplicates, molecules with high molecular weight, and finally vectorized SMILES. So in our work, we have developed two models. The first model is a simple, basic, unsupervised vanilla autoencoder that uses reconstruction loss and is aimed at being able to reconstruct the output, on the output to reconstruct the original SMILES vector. Second model is a semi-supervised autoencoder model, and it uses an additional neuron on the latent layer that's responsible to the ligand-protein interaction energy, which is called the free binding energy. And during the training of this model, this value is passed to the neuron on the latent layer. You can additionally see it's not connected to the encoder, only to the decoder. So this is done so that the decoder, instead of just trying to derive binding properties of the compounds from the embeddings on the latent layer, the decoder will simply get this value from the neuron, and in the generation turn, we'll be able to produce various compounds with the with properties of energy that we provide to that neuron, at least close to the given energy values. So I'll just quickly mention SMILES embeddings. So since we use this autoencoder as a generative model, we obviously use decoder as a generator in the generation procedure. So what both of these models actually allow to achieve is to create a molecular space on the latent layer, or so-called embedding space, or in our case, these are molecular embeddings. It is particularly useful in a well-known concept which came originally from natural language processing, and we're doing a very similar thing here. So we created a space which we can use for mapping our molecules, and then we can generate from this space. And in the best case scenario, of course, this space should have several metrics, right, that we can introduce in the space, and molecules with similar properties, especially in terms of our task that we are considering here, the binding properties to a specific protein. The molecules that have similar properties are very close in that space. So let's move on. So it should be noted that we also train an additional regression model to predict the free binding energy value, or the affinity of potential inhibitors in terms of the generated target. Sorry, in terms of the target considered, right? So we usually the validation of results, and the most important validation is, of course, the docking procedure, which more accurately estimates the energy. But we needed an opportunity to filter out compounds right away from the output of the generator, of the decoder, in the generation procedure. So we implemented this additional model as well. So it is done to improve the capacity of promising compounds that we can evaluate with docking. We can basically generate 1 million compounds, then we can filter out only the best, several thousands of them, based on this regression model estimate, and then we can move to docking and dock only the best compounds. So of course we needed several baselines, so to speak, to consider, or I should say several metrics to consider when evaluating our model, right? So the first, as I mentioned, was predicted energy, which we used to filter out compounds. Then for the compounds that we generate, we used the generated energy property that was passed to the neuron in the semi-supervised model, semi-supervised autoencoder model. So then we had another procedure for generate compounds, which relied upon generating new compounds based on the existing ones. So we calculated embeddings for existing compounds. Then we tried to add some noise coming from random normal distribution to those embeddings, and then we tried to restore new compounds, which should of course be similar to the compounds that we used as source compounds. And then our main estimator, or main benchmark, was of course the binding affinity estimate using by Autodoc-Wiener. I need to mention that those are preliminary results. We have presented these results at the PRIP conference recently, but we have gone further with generating many more compounds, and we will, I believe, soon likely have a publication that will include our most recent results. So these results are not recent, not the most up-to-date. But still, they are of course very representative. So what do we have here? We, as I mentioned, implemented two models, right? The first is vanilla autoencoder. The second one is a semi-supervised autoencoder. And we also utilize two ways of generation for both models. So for first model, we generated from random numbers coming from normal distribution. We fed those numbers to decoder. Then we used source compounds with the first autoencoder model, Then with the second model that we called the energy model, which has this additional neuron, we also tried to generate from random, plus we provided an energy threshold value to the to that particular neuron. And also with the energy model, we tried generating with from source compounds, plus manipulating some energy to the neuron ontolated layer, like increasing the energy threshold or decreasing or staying the same. So I know I don't have much time, so I'll quickly go through the table. So speaking about the first row, despite the fact that this model doesn't take advantage really of neither source compounds for generation nor any binding energy values, it's still capable of generating new potential inhibitors of the chosen target by just merely generating compounds from random. So you can see we have a lot of compounds with less than -8 kilocalories per mole, which is already considered to be good binders. I think -6 is approximately the threshold for compounds to be considered. At least they bind with the protein targets. So less than -8 is actually good, and we have several compounds which are less than -10. So speaking about the second model, this generation method utilizes compounds that we already have at our disposal and try to generate new compounds from them. So you can see that the share of generated compounds with high binding affinity is considerably larger, more than 38%, less than -8 kilocalories per mole. So the lower, the better. And 4%, if I'm not mistaken, of compounds showing the results of less than -9 kilocalories per mole. So next we have our energy model, and again generation from random. So the semi-supervised model, if people are familiar with computer vision, we utilize a version of style and content disentanglement, but we do it for molecular data, basically. So according to the results, we have 31% and 64% of generated compounds to be within the deviation from our energy threshold equal to 1 kilocalories per mole and 2 kilocalories per mole respectively. So 31% within 1 kilocalorie per mole and 64% within 2 kilocalories per mole. So next, moving to our last model, which we, at least for now, consider to be our best model. This combination of model and method gives us the top compounds, as I mentioned, in terms of the at least energy distributions. And 52 of all generated compounds are located within 1 kilocalories per mole from the source compounds, and 16% of generated compounds are lower than -9 kilocalories per mole. And as you can see, 40% less than -8 kilocalories per mole. So we've got a lot of other interesting results. We still have a lot of work to do in terms of comparing these models. So I'll just show you a couple of graphs. So first of all, as I mentioned, we utilized another machine learning model that was trained to predict the binding affinity of newly generated compounds. And you can see there is a clear correlation between the given predicted energy of new compounds and free energy estimations by the docking software. So we managed to do that quite well too. So then if you look at this plot, which is a distribution of three, the upper plot is a distribution of 3 energy. So basically we have a predicted energy distribution, right? The binary energy distribution estimated by our docking software, and also source compound energy distribution that we used for our energy model when generated from new compounds. And first of all, at first look, it doesn't seem like we're doing a good job, right? But then obviously we have a lot of errors that accumulate on different steps that do not play to our advantage. Like we train our model, which is of course not perfect, then with docking, which has errors as well, right? So we also are affected by the errors of the docking software, and usually the effect is to the worst side of it, not to the good side of it. So of course it would be a miracle if we could generate the compounds that are only better. But if you plot the distribution of difference of energies, of source energies minus energies generated, we can see that though the mean is about like 1.2, maybe 1.5, we have quite a few compounds that we generate with energies better than the original compounds. So -1 basically means that we generated quite a few compounds that have 1 kilocalorie per mole energy better than the original compounds. So, even if this percentage is small, we can immensely benefit from it. We also have a lot of different results in terms of comparing all the based on all the metrics that we used. So I think I don't have time to comment on this plot. But basically, you can see that we can observe that with lower energies, which again lower energy is better, we can see less variance in terms of energy deviations when we generate new compounds. So this is also something that we want to look at closer. So on this note, I will wrap up. You can read through our acknowledgements. Yeah, thanks for everyone here. We have some team members that weren't mentioned on the second slide, so you can see them here. Also, of course, huge thanks to our supervisors, Dr. Alexander Andrianov and Dr. Alexander Tuzikov. And thank you to our supporting organizations. Thank you.
Okay, thank you very much, Nikita. Thanks a lot. Maybe there are questions from the participants of our conference, please.
Yeah, I see the hands from BASNET. Would you like to ask something?
No, I was clapping for the representative. It's just a remote reaction.
Okay, so I have a question for Nikita. Have you ever tried the different energy circles for the generation in order to compare results?
Sorry, could you come again, please?
Yeah, I asked you, have you ever tried to set different energy circles for generation in order to compare results?
Yeah, we actually had this slide on our previous presentation. We decided to cut that one in particular since we have had less time for this one. This is also what we're of course looking into. We did experiment with trying to set different energy thresholds. If I go back to this slide, of course, of course we experimented with trying to set different thresholds for this energy neuron. And we do have some results that confirm that there is a difference in distributions in terms of compounds generated with different thresholds. We can't confirm yet that the result is statistically significant. So these experiments, I don't think were done with enough number of compounds. So as I mentioned, we have gone further with this work, and right now we have actually generated several dozens of thousands of compounds, and we are in the process of doing docking for them. So after we do that, I think we will definitely be able to say whether this works well and whether there is a statistical significance in difference between the compounds generated with different thresholds.
Okay, thank you, Nikita.
Okay, Nikita, one more question. These network parameters which you get at learning procedure, they depend on the target, virus target you used to find inhibitors. And in your research, which target do you use? I mean, for coronavirus?
Oh yeah, it's. I think I should have mentioned that it's the main protease of the coronavirus. So with this particular work, main protease. Yeah.
Main protease.
Yeah, main protease.
Main protease. You not. Okay, so you do not use S protein on the envelope.
No, not in this work. So yeah, as you said,
I'm sorry, we have to move to another
Sure.
presentation. It's already time for the start the next one. So if you can ask something short, yeah, let's do it, and we will start with the next presentation.
No, I think that it's good to like finish at least the sentence and then to move to another presentation.
Yeah, I just wanted to mention that of course this model is target dependent, so it's not universal, but it's universal in terms of if we have data from the screening stage for any target, we can utilize this model as far as there is enough data to train a deep learning model. So we will actually we're planning to utilize this model for spike protein as well, also for HIV targets and for other targets that we work with too.
Okay. Thank you very much, Nikita.
Thank you.
And Artemy. Now we can move to another presentation. Thanks a lot. The next presentation is development of a neural network to predict the likelihood of EGFR inhibition, and will be done by Grigory Nikolaev. And Grigory Nikolaev is a researcher at the United Institute of Informatics Problems. He recently graduated his postgraduate study and prepared his PhD thesis, and now is waiting for defending procedure. Okay, Grigory, please start.
Hello, could you hear me?
Yes.
Okay. Okay, I want to present you this work and some words about the protein target.
Sorry for distracting you or interrupting. You are showing the PowerPoint window and we don't see you the whole screen. So
then I'll just zoom in this way. Okay.
Okay, as you wish.
Thank you. So what is the EGFR? It is a transmembrane receptor that is activated when it binds to epidemical growth factor, transforming growth alpha factor alpha-rulin. When EGFR is activated, a cascade of biochemical reactions is triggered inside the cell, leading to an increase in the proliferation of tumor cells, tumor growth, simulation of invasion processes, pathological angiogenesis, and metastasis. Numerous biological studies have revealed increased activity of the EGFR receptor, and the cascade triggered by activation of this receptor in patients with non-small cell lung cancer. So now some words about SMILES feature matrix that were used in this work. SMILES is simplified molecular inputs line entry system. It is a way to represent the molecules in silico study. This method uses a strict and detailed set of rules to interpret the molecular structure into the chemical notation, which is user-friendly but also machine-friendly. In particular, SMILES notation for a molecule is a chain of character which is specified for atoms, bonds, branches, cyclic structures, disconnected structures, and aromaticity. Professor Hirahara developed SMILES based feature matrix to train a convolutional neural network model for predicting toxicity. His model outperformed the conventional approach and performed comparably against the winner of TOX 21 data challenge. Then some words about molecular descriptors. Molecular descriptors are terms that characterize a specific aspect for a molecule, including substance constants and whole molecular descriptors. Their calculation of former type derived from the difference in functional group substitution into the main core of the compound. Based on this approach, later in the expansion of the substituent constant. However, some whole molecule descriptors are developed from totally new methods or based on the physical experiments. Here you can see the structure of baseline model and it consists of the convolutional neural network branch that includes SMILES feature matrix, attention mechanism, and molecular descriptor. The SMILES feature matrix was flown through two CNN blocks, each consisted of two deconvolutional layer, one batch normalization layer, a dropout layer, and the max pooling layer before being flattened and fully connected in a linear layer. Then attention mechanism, it put attention or weight to the atoms in the chemical, which are represented by rows in the SMILES feature matrix. The larger the weight of an atom is, the more contribution of which atom contributes to the drug. By doing this, we can extract each competence weights for interpreting the results and analysis. The molecular descriptor branch is used to train the molecular descriptors data. And concatenation when where three vectors that we get from molecular descriptor, attention mechanism, and from the SMILES feature matrix are then concatenated to form the final representation vector. This vector combines information from both molecular structural information and descriptors information. Then I try to make the prediction of this model a little bit more better. First model, I use n-grams to extract information about specific regions of SMILES in the hope that this would improve the prediction of the model. The best model was obtained when I used 3 grams. Then one more model, second model, I took BERT model and edit it to the baseline model. KBERT, one of the first attempts to systematically evaluate transformers on molecular property prediction tasks. While not at state of the art, KBERT scales well with pre-training dataset size, offering competitive downstream performance on molecular net and useful attention-based visualization modalities. Here on this slide, you can see the results of testing these models. As you can see, using KBERT plus baseline model, part of the baseline model, do the best precisions. As some words about training and testing sets. The training set includes 3,500 molecules, of which 500 were inhibitors and 3,000 were not. The inhibition activity of a particular substance was assigned if its IC50 is less than 10 nanomoles. Then we to make validation, I use molecular docking methods. I use program Qvina to simulate molecular docking, and like additional evaluation function, I use NN score 2.0. Here on the slide you can see the 10 best compounds and also the structure of best scoring inhibitor. In the next slide, you can see the whole results of 70 molecules that were randomly selected and docked and reevaluated. As you can see, as you can see on this slide, we can set that if we have score log reg more than 0.5, we can say that it will be probably inhibitor. So it will be a potential inhibitor, and it makes sense to check it using molecular modeling methods. And as last slide, here it shown the results of docking of the best inhibitor based on the results of validation, and the ATP molecule with which the inhibitor directly competes. So that is all. Thank you.
Thank you very much, Grigory.
Thank you.
Maybe I would like to ask people participating for questions.
Hello?
Yes. Yeah, hello. Can you speak a little louder?
Yeah, do you hear me now?
Yeah, now it's good.
Okay, I have several questions. The first questions, my first question is, I'm a little bit confused whether you have used some parts of SMILES as a dictionary to vectorize and to feed it for the network, or have you used molecular descriptors? Which one? Because you have presented both options, but which was the basement for your network?
Okay, thank you for a question. I use the part of the smiles when I try n-gram plus EGFR model. Then I use n-gram instead of molecule descriptors. But in another models, I use molecule descriptor and these molecule descriptors from the library MoldRed. It consists from a lot of different parts and okay, there are more than 200 different attributes.
Okay, okay. I have also another question. Could you please show slide number 9 with the results of docking? And you here have used 2 scoring functions. That's a very interesting question. How you have selected your top 10 best compounds? Have you used some consensus techniques? And if yes, which? Or
I just rank them in the by an n-score function.
Okay, okay. So am I right to understand that QWinner is provided just for comparison? Yeah.
It's just for comparison with the results of an n-score, and also on the 10 slides, that is also the result of an n-score here.
So, okay, and my last question is, I'm just curious, why ATP? Why you compare your results with ATP molecule? Why you have chosen this benchmark?
Because the ATP molecule is a molecule that always binding to the EGFR. And if we want to block EGFR, we just should compare it with the ATP molecules.
Okay, thank you very much for your answers.
Thank you for questions.
Thank you for the presentation.
Okay, are there any other questions? Please.
Yeah, I think I have one little question. So as far as I understood, you predicted not the value of energy, but you predicted the activity. So you used it as a classification problem, right? So you try to predict whether the compound will be active or not.
It's a probability of it would be a potential inhibitor or not.
Yeah, I see. Thank you.
Okay, thank you very much. Other questions, please?
Yeah, I have a question. What do you plan to do next with that compounds? I mean, with your best 10?
These best 10 compounds, I will do nothing because there are known inhibitors. In my plan, I want now to use virtual screening, and with this neural net model, and then docking for the best compounds, and then molecular dynamic and so on.
Okay, thank you for the answer.
Okay, thank you very much, Grigory. So we can move to the third presentation of our meeting. The third one will be done by Timofey VAITKO. Timofey is a third-year student of the Belarus State University, and he will present his report titled Heteroencoders for Computer Modeling of Potential Drugs. Please, Timofey.
So hello, my name is Timofey VAITKO. So can you hear me?
Yes.
Yeah,
yes.
we can hear you.
Can you see me?
Yes.
Okay, that's amazing. Okay, let's start. Hello everybody again, my name is Timofey VAITKO, and today I'll show you something that really matters. So my topic is heteroencoders for computer modeling of potential drugs, and to be more detailed, we will talk about the leukemia problem and about how we can solve it. So let's start. This is our concept for today. There's a lot of them, but actually it will be a drug design part and machine learning process part. So let's start. Okay, drug design. First of all, drug design is an intensive process of finding new medications based on knowledge of biological targets. In the most basic sense, drug design involves the design of molecules that are complementary in shape and charge to the biomolecular target, with which they interact and therefore bind to it. Sounds so simple. Yes, we need something like have a target, a special ligand, plasma, and have a complex molecule. Yeah? If we look at that, it's really simple, but it's actually not as clear as it sounds. And if you want to be correct, it's better to say ligand design, because ligand is what we're looking for. Ligand is molecules that will bind tightly to its special target. So drug design is something like a misnomer, but for now, I think it doesn't matter. Leukemia. So leukemia is cancer, okay? Cancer is a generic term for a large group of diseases that can affect any part of our body. One different feature of cancer is the repeat creation of abnormal cells that grow beyond their unusual boundaries, and which can then invade adjacent parts of the body and spread to other organs. For statistics, 10 million people died from cancer in 2020, and acute leukemia kills about 400,000 people every year. So that's a real world problem. Leukemia is a group of blood cancers that usually begin in the bone marrow and results in high numbers of abnormal blood cells. Unlike other cancers, leukemia generally doesn't form into a mass called a tumor, and that can be seen in image tests, for example, like X-ray. There are many types of it, and treatment depends on type of leukemia you have and maybe other factors, how old are you, and others. Nowadays, there's 3 main types of inhibitors, but they aren't able to block any leukemia mutations. Main aim of our work is to build up a multi-kinase inhibitor, which will be unique for every mutation. Because last years, researchers have shown that various pyrimidine derivatives are excellent inhibitors and are currently used in the treatment of some types of leukemia. And because of it, we will try to build our inhibitors based on pyrimidine derivatives. So how do we want to create our solution? And what do we want? We want to build a generative deep learning model which will be able to generate new ligands for leukemia. Our main goal, find new most effective multi-kinase inhibitors which are based on pyrimidine. For now, we have obtained more than 500,000 pyrimidine derivatives from open chemical libraries, more precisely their properties and presentation in various formats. But after cleaning them for our analysis, we have only around 100,000. Yeah? As inputs of our model, we have chosen 2 string formats, smiles and calculus smiles, and indicated characteristics of each molecule. About our model chocolates, and in output, we expected only these 2 string formats, as I mentioned before, smiles and calculus smiles, which will be calculated from 1 latent vector. But regardless, so how our solution steps looks like. First of all, we need to collect data, as I mentioned, split data into 3 inputs for our neural network. It will be 2 string formats and 1 feature set. Okay, we will build some get-to-encoder models that we'll talk later, and it will be able to generate new molecules. So after that, we will create a good space representation for our test set, and about this also later. So after we create a representation of latent space, we need to generate new molecules, and next, prepare research. We'll explore our results with bioinformatics tools. We need to maybe all drug design steps for analysis of results. So, okay, but now let's something about preparing our model. Let's talk about machine learning concepts, just only for reminder, yeah? Let's go through main concepts. unsupervised learning, machine learning field, which explore tasks where only things that we have about our data are descriptions for our data. And by this, we understood that we have some pyramidal derivatives, and what we expected in outputs, new pyramidal derivatives, so it's unsupervised learning task, yeah? And for example, here are some other types of unsupervised learning task, yeah? So it's association rule search, anomaly detection, dimensional reduction, clustering, generative models, and segmentation. And for our goals is generative models. So, okay, generative models are usually stands nearby deep learning models. And let's review some deep learning concepts. Neuron. Everybody knows how it works, linear function and activation function, nothing else. If we combine them, we will get fully connected neural network. There is one good theorem, which is exactly proof of power of neural network and proof of power of our work. So it's a universal approximation theorem. A fully connected neural network with input, dense, output layer can approximate any continuous function of any number of varieties with any precision. Based on this theorem, we can assume that we can get good encoder and decoder networks as well as context latency space of our data. So we'll fit our model with BERT propagation. Everybody knows how it looks like, and that is the best way to feed neural networks right now. That is so mind-blowing that we can solve an unsupervised learning task with BERT propagation of weights, but that is specific to this task, yeah? So, okay, to build getcher encoder, we need to know what is autoencoder. And so I told you that we need BERT propagation of weights, yeah, and autoencoders here are. Concept of deep learning models, which contains two parts, encoder and decoder. As idea, build the most effective encoder, which will be able to compress data informatively, and then a most efficient decoder, which can recover the data. So for this concept, our right answer for our data is our data. With an autoencoder, we can sort of task. If we are good at representation of our latent space, we will be able to generate new molecules by processing points from latent space with the decoder. But as you can see, there is only one type of input available. And if you want to build a more representative latent space and more complex model, that will be so hard with autoencoder. But despite the simplicity, there are a lot of autoencoders in real life. Usually it's always dimensional reduction, generative models. I did them for maybe more strong models. Also, you can achieve information retrieval and dimensional detection and a lot more. And now, get your encoder. What is it? So we want to be our autoencoders more powerful. And what if we combine them? That is not as we did in fully connected neural network with neurons, but there are several similarities. For every input type, we have each own encoder. And for every output type, we also have each own decoder. So what can we achieve with it? More representative latent space for first, more results from one latent vector. Imagine you have only one point from latent space, and after that you get m outputs. So that's in m phrases effective than autoencoder, yeah. So it also will be computationally cheaper to use some basic encoders and decoders and get your encoder than use one strong encoder and decoder and autoencoder, yeah. So also this will protect us against fading Gaussian problems because we don't have strong layers, we have some basic encoder and decoder. Okay. And also there are a lot of distributed encoders. Maybe they're the same to autoencoders. The only minus is that it can be, but it's also a plus that you need to collect more data to train your getcher encoder. Okay, our model. With this model, we're trying to generate new molecules. Let's go step by step through them. We have 3 encoders and 2 decoders, and so I'm trying to work with it. Let's look at encoders. For calculus smiles and smiles, we have same encoders, which contains of 2 LSTM layers. It's a long, short-term memory layers. And please notice that from every layer, we get states of long and short memory and put them to concatenate layer. And second LSTM takes outputs of first LSTM layer and put states to concatenate layer. write this solution for these encoders. There are no secrets that one of the effective tools in string processing, remember calculus smiles and smiles are string type of data, yes? So one of the most effective tools with string processing neural networks is recurrent neural networks, and usually power is manifested with LSTM layers. Yes, they're so effective because they choose this. And as you can see, there are only 2 LSTM layers for one encoder. Okay. For characteristics, we built a fully connected neural network with 3 dense layers and 1 batch normalization layer just for normalization. So then we combine them in concatenated layer. Then we put them again in batch normalization layer and to a dense layer. So output of our dense layer is our latent vector. Okay, decoders for calculus and outputs we expected only for calculus smiles and smiles string formats, yeah. So the decoders for them are also the same. We get from our latent space states for LSTM layers, process them with dense and batch normalization layers, and then put them to the LSTM layer, as we can see on the slide. And to build them effectively for the LSTM layer, we put string inputs for smile decoder, smile inputs for calculus, calculus rendered. That is a trick for building good latent space in total results when we feed our get-your encoder. So after that, we'll split our model into 3 models. Yep. So but for generation, we don't need them at once. Yeah. So first model will be encoder. It will be the same as you see. Yeah. Second, it will be latent to states model. So it's this part before LSTM. It will calculate states for LSTM layers of decoders. Third, it's 2 same decoders that will get states from previous model, and for string input that they expect only one hot encoded char, and output also will be 1 char, so next char of our molecule. So maybe you can ask why we feed with full string, and when we split models we need only 1 char. That's the idea of char by char prediction with states, so it generally works better. And we will assign LSTM weights from pre-trained get-your encoder to our new decoder that will generate molecules from latent vectors. Okay, so that's also about our analysis of results. After fitting process for our model, we have good results in terms of machine learning. Last function for our model with categorical closed entropy. Yeah, so that was our last function. Loss on trend is around 50 hundredths, and on the test it's 57 hundredths. This is summary of 2 outputs also. Yeah, remember we have 2 string formats and outputs also it's a sum. We generate 93% inhibitors by our model, and now they are in the processing step. So in processing step, I mean all of drug design step, such as docking and others. So, okay, let's get the conclusion. Why we have chosen get-your encoders? We had an aim to build a strong, powerful, universal solution that will be easy and fast to fit on a new data. As you can see, there are no specials for them. Yeah? Also, we wanted to build more representative space and build more outputs. So by this, we choose get-your encoders, and it's work. So that's all for today. Those are my contacts, so it will be a pleasure for me to talk with you later. And now, if you have questions, I will be happy to answer them.
Okay.
Thank you, Timofey.
Thank you very much. Any questions, please, dear colleagues? Because Timofey is only a 3rd-year student, right?
Yes.
So have you implemented all these procedures which you explained us now?
So with drug design parts, I'm very thankful to Anna KARPENKO. She is my science director right now, and from
Because you already spoken about the results, I understand that you already have this model implemented, right, or not?
Yes, yes. So we already feed this model, and now we're processing our results. They're not ready to. We're not ready to say is it a good inhibitor for now or not, but in a short time, I believe that we will.
Are you also told that it's very easy, even 25 minutes to to adapt this model to other, for example, targets. It's okay. It's true.
Yeah, that's true. I can show screenshots for you. For feed this model, we're in a specific surface called Google Colab. I need only 25 minutes. Yeah. So I think it's amazing.
Okay, it will be very interesting to discuss with you, like not online but offline, your results. Okay.
Okay.
Maybe other questions, please. No questions. So thank you very much for your presentation. Yeah, at least as far as I understood, at the third year you like at the Department of Applied Mathematics and Informatics of the Belarusian State University, you had no preliminary knowledge about these areas of molecular modeling and so on. So you are very fast, I think, in your implementation and research. Okay, very good. Okay, thanks a lot. Goodbye.
Okay, I have some thank you words for Anna Dmitrievna. I'm so happy to be there, and for me it's a great opportunity to say something to people with my neural networks. That for me is her crossroads. So thank you so much, Anna. Yeah.
Okay.
Thank you for the kind words. Glad to work with you.
Thank you. So we now are coming to our last presentation. It will be done by Dr. Roman Sergeyev. The title is Microbiome-based disease prediction. And Roman is a research scientist working now in Germany and NEC Laboratories Europe in Heidelberg, Germany. Previously, Roman was in our group and defended his thesis here in Minsk, and then recently he moved to his new place for postdoctoral position. Please, Roman, it will be very interesting to listen to your new presentation. Okay, please.
Thank you. So. Can you hear my screen, my presentation?
Yeah, we can see your screen.
Yes, okay. So, yes, my name is Roman, and today I wish to tell some words about the work that I'm currently doing with a team in NEC Laboratories Europe, and this work is related to microbiome-based research. So, we are trying to apply machine learning methods to solve biological problems, and now microbiome is a kind of hot topic because it seems to be that microbiome is a very important predictor of many states or of many processes that take place in the human body. So just a very brief introduction in this domain area, because I suppose that not everyone knows about microbiome a lot. So briefly, the microbiome is assumed to be all bacteria, or not only bacteria, but all microorganisms that may include bacteria, virus, fungus that reside in our body. And you can see that we actually get those microorganisms due to various factors. It can be defined by host genetics, by the diet, what we eat, by the lifestyle, environment, and by some even industrial factors. And those microorganisms reside almost in all parts of our body, including nasal, oral, lungs, stomach, intestine, skin, and some others. And they all play a very important role, which is not really clear enough up to our days. However, most researchers now study so-called gut microbiota, so the microorganisms that live inside our intestines, mostly because they are really available for this study, and you can do just the biopsy and do the sequencing and to understand what kind of bacteria are there. In recent years, there are a lot of studies that try to show how microorganisms are related to our disease states, to our maybe metabolic states, even mood, because there were papers that prove that microbiome is something that can even define whether you are going to get depression or mental diseases, and it can be a very strong marker or very strong predictor. And also another hot topic now is that how to understand how microbiome is related to cancer and to the response on anti-cancer therapy. And it's not wonder why it plays an important role, because if to compare with our own set of genes that is in our human cells, we can see that we have 10 more microbiome or bacterial cells living inside us comparing to ourselves, to our host cells. And it brings, in comparison, so if a human naturally brings at about 20,000 genes, then the bacteria get us more than 3 million genes. So you see that microbiome is very important part of every human being. And also the last but not least interesting thing that even if we all human, you, I and all the others participants, maybe in more than 99% of our genetics seems to be very similar or the same. I would say the same. If we will consider the microbiomes, probably we will be different on 80 or 90%, up to 90%, if the study will be based on understanding the exact microbiome or profiling the exact microbiome. Okay, and here we are concentrating on the disease prediction task. We try to understand, based on the gut microbiome, whether it provides us a good marker for some diseases, and how machine learning methods, first of all, deep learning approaches, can help us to do the predictions. And we also tried to show that deep learning is not just a black box, but we can get some explanations, and we can understand which features were important and which features were less important to do the inference. So here I will mostly speak about this paper that now is available publicly via bioRxiv. And it is called Microbiome-based disease prediction with multimodal variation information bottleneck. So this is a modification of variational information bottlenecks approach that we did here in order to combine multiple dimensions. Okay, now I will come directly to describing the method. And I would start from the data set that we were using. So to train the model and to do the predictions, we used publicly available data sets that I processed on my own, mostly. And they included seven different diseases, like inflammatory. So there are abbreviations, but I will clarify a little bit. So IBD means inflammatory bowel diseases. This is a disease of intestine. Type 2 diabetes, T2D, yes, it's just type 2 diabetes. There are two different cohorts. Obesity means obesity. Cirrhosis is liver cirrhosis. Colorectal refers to the colorectal cancer, And hypertension refers to hypertension. So what we did with the raw data, we extracted, we downloaded from NCBI the archives that contained the results of metagenomic sequencing. And then we did some pre-processing to get the so-called microbiome profiles, which we used as the input to machine learning models. And here is a little more details about the whole procedure. So normally you extract from the biopsy the DNA that are in, you fragment it, and you do the sequencing. So you remove all human reads in order to get there only the bacterial reads. Then we did pre-processing. We used already established tools and pipelines in this field to do the steps like quality control, data read streaming to get rid of bad reads. And we did the profiling to get two types of, so in the basic solution to get two types of profiles. So one type of profile, so-called species relative abundances, and the other profile is so-called gene markers. So, and here is an illustration. What is it? So species level relative abundances are just the list of species that were found in the sample, in the probe. So here in the column, you see the sample. And you just try to calculate how much you have that species in relation to the others. So if to sum up the whole column, you will get 100%. And here you just see the distribution, which species and the percentage of a species in each sample. The other type of data has a little bit other nature, so it is not continuous data now, but the discrete, which just shows us which marker, which identifies normally some kind of gene or the important region of bacterial DNA, which can be used to identify the concrete strain of the bacteria or the species of the bacteria, but normally it provides a resolution, may provide the resolution up to the bacterial strain. And you see just the indication of whether this marker was found or not found in the whole soup of metagenomic reads. So in general, we have some soup of metagenomic reads from the sequencing machine. And now we just do two kinds of methods to extract the information about which species and what are they prevalence comparing to each other, and the other type of information which genes or based on which gene markers are in this soup. And here I wish to now to continue with the basic idea that lies inside the approach itself. So we, as I mentioned at the very beginning, we're trying to solve a classification task. So we are trying to understand, based on the analysis of those two types of microbiome profiles, whether the patient is healthy or sick or affected by this specific condition, which can be IBD or colorectal cancer or hypertension, depending on the cohort that we discovered. So it's a binary classification problem in the essence. And here is a brief a piece of theory behind the methods that I wish to introduce, which is called variational information bottleneck. So the idea is the following, that we wish to use autoencoder And in the autoencoder, as you know, you have so-called latent space, which refers to that. And you wish, on one hand, to have as maximum information about the final label, about the class in this latent space, which contains the compressed information from the input. But on the other hand, because it will be just trivial solution in this case, you should try to obtain the latent space such as it will be maximally compressed about the input X. And here we construct such kind of objective, or the function that will optimize in respect to the parameters that will leverage between those two objectives. And in the end, if we rewrite this expression, we can construct the last function for our autoencoders that we are going to train. And the last function, if to write everything accurately, also taking out that we may have variational approximation of the probabilities that will be in the formulas, we will get this loss that can be represented like in this expression. And now we are going to work with this part. KL refers to the Kullback Leibniz divergence because this formula was taking account only one type of data that you can get as an input. And here is how we are trying to make this method not just working with one type of data, but to make it so-called multimodal, or to allow input from various types of dimensions, various types of data. And here is the trick how we approximate this probability in Kullback-Leibniz divergence. When we have multiple dimensions on the input. So basically we work with those probabilities, and this lead to slightly altered loss that we will try to minimize, which will look like this. So all the details can be found in the paper, so I will not, I wish not to go deeper. But so the general the general sketch of the model look like this. So on the input you have you may have several modalities with different types of data. It could be continuous data, it could be discrete data, binary data, it can be some other data. Now you have on the input encoder for each data modality. In the middle, you apply reparameterization trick because it's a variational autoencoder. And you do this trick with the product of so-called product of experts when you do approximation of the probability in the latent space, in the latent layer. And in the end, you will get some approximation that consists of the product of experts that came from multiple dimensions, multiple data dimensions. And then you, on the decoder part, so you may apply any task. It can be regression or classification, but in our case, it's a classification. And you are just try to optimize the last function that I showed here. we implemented this approach and compared it with how it performs related or exposed to the state-of-the-art approach, that the approaches that include some that's based on deep learning methods, and also that are based on conventional methods like random forest, because in most publications it's claimed that random forest is really, despite its old, but it still provides state-of-the-art results in microbiome classification tasks. And here we can see that in many data sets we have very comparable and even better results with our multi-model approach. And however, this is not only, maybe this is not the main objective or the main goal that we wanted to achieve, so to create the method that will beat all the state-of-the-art, but we also wanted to add some level of explainability. So here you can see also how we can visualize the latent space or what's happening on this level. We call it latent encoding during the training. So here is on the right is a kind of conventional approach to visualize the encodings of the latent space, and it's normally based on, you just do the PCA from the input and you try to understand whether the classes are separable or not. So in our case, we can see that if you just plot the points, the projections of the input points in the latent space, you can get more clear evidence how the classes can be separated. Here's another type of diagram that we can also plot from this method. It's also plots the confidence interval on the test data. If here we try to do experiments with different kinds of loss functions, and for each loss function we can get a separate plot that shows us not only the points in the space. So this is not the all patients, this is only the trained, not trained test set, but also the 95% confidence interval. So how and you can have the feeling how our prognosis, how our predictions are confident, how we are confident about them.
I'm sorry, Roman, yep. I want to tell that already time is left.
Okay.
So we have time for a question. We can take that time, but not more than 3 or 4 minutes.
Okay, okay.
Finish, okay?
Okay, another kind of experiments was to compare whether this mixing of several multiple modalities really helps us, and we see that at least it does not drop down the performance of the method. And for the explainability part, we used the methods that is used applied in image processing, and we try to understand at which points, at which samples the model looks in order to get the labels. And this we can use to get the most important bacterial species to do the predictions, to understand whether the patient is healthy or sick. And we can see that if to check it with conventional statistical tests, that the most important species, according to the conventional statistical tests, are also on top in most cases of what our model looks in order to do the predictions. And maybe one of the last slides about the performance, if to compare with also another method and with conventional methods, we can see that here you do not need to train a lot hyperparameters like in random forest, and actually the time does not increase much when you add more and more data modalities. So in summary, I would maybe articulate a little bit that here we just developed a multimodal learning approach based on birational autoencoders that allows you to combine different data modalities and to do the prediction task or to do the regression task. And here we try to apply this approach to analyze microbiome in order to predict the disease state of a patient. So that's all from my side. Now, I'm happy to hear some questions if you have. Thank you.
Thank you, Roman.
Thank you very much, Roman, for your interesting presentation. Could you tell me, in your research, how many modalities of data you used?
So now here we used up to 3 modalities, 2 microbiome modalities coming from metagenome sequencing and 1 modality that came from metabolome, because so the reason is that normally the main limitation on how many modalities were used is the data itself. So on one hand, if we add some metadata like the patient status or health records, which is also possible, it means that probably they will contain information which is really defines the disease status better than just looking into the microbiome. However, if we use only microbiome-based modalities, we can only get the data that come from metagenomic sequencing or metabolomic. But this is important because now it is published that microbiome may interfere with the immune system of a human, and the immune system, of course, interfere with for example, cancer tumor, or it can define how the organism battles against some disease, and this interaction is applied via metabolites. That is why it is important to have a method that can analyze together metabolites and metagenome sequencing, so to understand which genes are there, which species are there, and which metabolites are there.
Okay, thank you. Maybe my last question.
Yeah.
Roman, as far as I've seen from your results, at least for 3 diseases, so the results tell us that these diseases are not explained or not correlated to this your input data, right?
Right, that's really so, and it's a good question why it is happening, whether it is the noisy data set or whether, so is it the bias that came from the method how those data sets were collected, or whether there is no real evidence that microbiome constitutes the main role in defining those diseases. It's really not clear why this is happening, but yes, you're right that for some diseases, it not only in our case from our method, but also from other researchers that we can see the similar results.
Okay, thank you very much. Okay,
maybe
there are other questions from audience.
Yeah, I would have a question. Hello, thank you, Ramon, for your talk. That was very interesting, and I was wondering, your data input is only whether there is a species or not, right? Or sometimes
No.
the relative abundancy, but not something like a genetic variance, right?
So I would say that yes, we used definitely abundances that is which species are there on the species level, and how much of this species relative to other species is there. But on the other side, we have so-called marker profiles. I think that for I don't know exactly how this database of the reference markers was compiled. It is from this Metaflan software program that is normally used in this field. But I do not exclude that marker profile may contain markers based on some variants. It means that if you have, for example, one species of the same bacteria, but two different strains, probably they will be different because of some variants. And this should be reflected in this strain level profile.
Okay, thank you. So you're accounting for everything which is in the profile, but if something's missed in the profile, it's also missed in the whole data set, right?
I guess yes.
Okay.
So normally I think that the problem also is how much we know about the microorganisms at all, because anyway, when you do the pre-processing, you align the reads to some reference genomes, to the genomes of reference bacteria or maybe viruses, I don't know. But however, if you do not have the reference, you cannot identify that there is some specific species or specific gene inside.
Okay, thank you.
Thank you very much, Roman, for your interesting presentation. It was nice to see you. Okay. Anna, so we can now finish our session. Maybe I would like to say a couple of words before I give the floor to you, because it was a very interesting session, like the first one, and I think it also was interesting for participants to hear our students and our guys, which already continue their research work after defending the theses. So I think that we can further also organize a similar session for presentation of own results of our students or some interesting papers, discussions. It also will be very useful for us to communicate in this way. So I would like to thank all the presenters at our session and also all the participants. We have many, at least I see that 33 participants also were at this session and 40 participants were at the first session. So I think that our seminar or our conference will be useful for our students. Thank you very much. Thank you. Anna, so I give the floor to you, please. Maybe Axel, you would like to say something or not?
Yeah, I would just like to say thank you for organizing. I think this was a very nice event, and I would be very happy if we could have such event, some follow-up event in the future. I think it's very nice for students at all levels to present, and yeah, this would be very nice to have a follow-up event.
Okay, thank you very much. Anna, maybe you can continue because you were interested to make a joint photo of all participants. I don't see Anna. Alexei, are you?
Actually, so I don't see Anna too. Well, yeah, we may do the same as we did at the end of the previous session, and we'll make a screenshot. Please, well, turn your cameras on, at least if you want to do this, and I will try to snap the screenshot now. You may do like this. Okay. Yeah, this is quite complicated because we have several screens of us. Because yes, I think the participants are quite the same. Yes, the same persons, at least. Yes, again. Yeah. So I did this. Yeah. So should we expect Anna again to follow up, or just to round up the session? No, we may finish. Please, Professor, you may finish, or we can do this.
Yeah. We can finish because probably Anna lost connection. I don't know what the problem. So I would like also to thank our sponsors and UIIP Connect project and JANT for providing this opportunity to use their facilities for this conference. So thank you very much.
Yes, I can just add that UIIP Connect project is a project which is under the umbrella of Eastern Partnership, big flagship project called EU for Digital, and it is done under JANT Association. Also, JANT Association is a networking association of networking providers who provide networking connectivity through the pan-European and network providers. And at least I think 60% of you already know about such kind of services like EduRoam, which is a free Wi-Fi service for students and teachers and researchers among universities. So it is JANT. It is JANT. So our partner, BASNET, which is a department of United Institute of Informatic Problems, actually is a partner of JANT Association. So we provide these services. I mean, BASNET provides these services in Belarus. And I hope that we will keep this project alive despite this different period currently we're experiencing, not COVID-19, but also this type of things which happen between Europe and Belarus. Still, I hope that our communication will be live in the near future. And as Axel said that we'll try to keep this activity alive. And I hope, if you do not mind, we will keep this title called STUDATA. Why not?
Okay. Okay. Thank you very much. Goodbye.
Bye-bye.